This conference will now be recorded.
Okay, so let's get started. Today mainly we are going to touch base upon graph and graph problems. Right? Although the topic name looks heavy, but ideally if you see, coding of graph will mainly entail using map, using lists, and third thing will be using matrices. Right? So we will focus on, like, leave the word graph aside, and if we focus on what exactly we are doing, you can say we are doing problems of map, list, and matrices. There is one getting started code that we have shared, because graph can have various representations. So this code is is taking some sort of input. You see, this first line of input is giving number of test cases. Then we are talking about number of vertices and number of edges. So ideally, if you look at this graph, how many vertices are there? How many nodes are there? 8, including 0 to 7, both inclusive. So we are saying 8 vertices. Edges wise, every line is telling which vertex is connected to which other vertex. So 0 is connected to 2. So we say C 0, 2 is an edge over here. Now, if this input is there, we can represent graph in various formats. That is what we talked about last time. So if there are 8 vertices in total, can we represent the graph as 8 by 8 matrix? 8 cross 8 matrix. Here this will be 0 to 7, and here this will be 0 to 7. If 1 is connected to 7, we will go and put 1 here, rest all we will make zeros. Right? Can we say a binary matrix can represent a graph? Right? Okay. That is easy representation. What if I say vertex numbers are not from 0 to 7, they are 1 to 8? Can we represent that graph as a 2D matrix? What size of matrix do we take? 9 by 9. So what we will do, we will take a 9 by 9 matrix. We will not use 0th column and 0th row because they do not mean anything to us. So we will go to first row, fifth column. It will tell us that 1 and 5 are connected or not. Now in graphs, this graph that we are talking about, this graph that we are saying, it's unweighted graph where just vertices are connected to edges. Unweighted graphs are where we do not assign any weights to them. In real world, what will be a good example of unweighted graph? Where things are connected to each other, but there are no weights associated with that. We talked about social network is a graph, right? Is friendship a weighted edge? This edge represents A is friend with B. This edge represents B is friend with C. Friendship will not have any weights. Can we say that? But what if these were cities? A, B, C, D are cities, and we say these cities are connected to each other by road. Can this have weight associated with it? What will be the weight representing? Distance is 1. Time. It is basically based on the problem that is given to us. It can be road distance, it can be flight cost, it can be time taken. Right? So graphs wise, when we do graph problems, we see graphs can be of various types. One is on weight. It can be weighted or unweighted. It can be directed or undirected. What is directed versus undirected? If there is an edge from A to B, yeah, you cannot go B to A. What will change if we are representing a graph? Let's say I draw a graph with 1, 2, and 3. This graph that I have drawn, this is what category of graph? Can we categorize them based on these 4 factors? Is this weighted or unweighted? Unweighted. Unweighted means the edges that are connecting to vertices do not have any weights associated with it. It just represents they are connected. It is directed or undirected? Undirected. When we draw directed graph, we say 1 to 2 there is a road, 2 to 3 there is a way, and 1 to 3 there is a way. This graph, right side graph, we say is directed graph. When we represent both of them with the help of matrix, what changes is we take a matrix 1, 2, 3 here, 1, 2, 3 here. I'm just leaving out the 0th row, 0th column, and 1, 2, 3 as well as 1, 2, 3 here. Now in this graph, we say 1 is connected to 2 and 2 is also connected to 1. That is what undirected means. So 1, 2 and 2, 1 both will get a value 1 here. This one is representing it is connected. 1 is connected to 3 also. 3 is connected to 1. 2 is connected to 3. 3 is also connected to 2. Now you go and fill zeros in rest of the matrix. So can we say this graph is representing undirected graph? Now how will directed graphs representation change? 1 is connected to 2, but 2 is not connected to 1. This edge does not represent that. Then 1 is connected to 3, 2 is connected to 3. So we understand the difference. If it is undirected graph, then we will put edge for if A is connected to B, we will say A and B are connected. That means B is adjacent to A as well as A is connected to B. So what is a good example of undirected relationship in real world? That means if you have that relationship with someone, that someone has same relationship with you also. Family tree, no. Your father is your father, but you are not his father, right? So that is not undirected. But yeah, the example that you are saying took very broad, but there are a lot of relationships which are undirected. Huh? Distance between two cities if they are connected to one road which is two-way, right? But if going side there is a different road, coming there is a different road. One-way traffic is an example of directed or undirected. One way is directed, right? Because it may happen that while coming you have to take extra road. So it depends. Yeah, cities. Friendship relationship in social network. If you become somebody's friend, he becomes your friend automatically once that is accepted. In social network, any directed relationship, Quora uses that. YouTube uses it. Follower, yeah. So if somebody is following you, it's a directed relationship. It doesn't mean you also start following him, right? So these are the examples in real world that we see the directed or undirected relationships, right? Okay. So when we do the problems, we will not go into nitty-gritty of all these things. Today our focus is mainly unweighted graphs. So we are not caring about the weights. But imagine if weights were also there, if these edges said 1 to 5, 1 to 2 there is a distance of 5, 1 to 3 there is a distance of 6, 2 to 3 there is a distance of 4. How can we represent that in the matrix? Rather than 0 and 1, can we directly put their weights? That will solve the problem. Here also 4, 6, 10, we can directly put. So this was all about adjacency matrices. But if we use adjacency list, we want to come to a simplest notation. For all these four graphs, we are clear, right? How to represent them in adjacency matrix. Now, if you want to use adjacency list, what is the simplest way using which we can represent a graph? So last time we said it will be map of any key. It should be key data type. Let me go with int right now. We are assuming they are ints. And list of int. But if problem statement says that this graph that we are giving you, it has vertices numbered from 0 to n or 1 to n. if vertex numbers are fixed, either 0 to n or 1 to n, then we can have simpler notation than map also. List of lists, we can say that, or array, because list of list means it's kind of list of all the lists. We can also say this is array. We can say, and here G becomes an array for us. So when we say int G, this is what we were discussing last time. This is integer array. When we say char G, this is character array. When we say list int G, it's an array which contains list of integers, right? So if we have to do coding problems in a simpler way where we are writing the code from the main function itself, we can stick to very easy notation, and most of the problems fall in this category. Now if G is an array where each element is a list, then how do I know if this is the representation imagine we are using? Give me all vertices connected to 3. How will I get that? This is the array. Vertices are from 1 to n. This array is representing the graph. How can I get all the vertices which are connected to 3? G of 3 can give me a list. If I print that list, they are the vertices adjacent to 3. Right? Now, what kind of graph are we representing using this, or what kind of graphs can we represent using this? Undirected, no weight. Because here what we are storing is, if 1 is connected to 2, we are saying 1 has a list which has 2 and 3. This is 1's list. 2 has a list which is 1 and 3. 3 has a list which is 1 and 2. Can we say that this is the representation of adjacency list representation of this graph? What will be adjacency list representation of this graph? 1 is connected to 2, 3. 2 is connected to, this is directed now. 2 is connected to 3. 3 is connected to, so 3's list will be empty. So this is for this. So we are able to represent any undirected or directed graph using adjacency list. But what if we want to store weights also in this? What if we want to store weights as well? Yeah. So basically from 1 to 2, we want to one time we want to say they are connected, and we also want to say they have a weight of 5. So what exactly we do now is this list of int that we were storing, we make it little complex list. We say list of, let's say we define our own class or structure, and this has 2 fields. One is the other vertex and another is weight, right? So now this list of edges is storing the graph information. How? If we see, if 1 is connected to 2 via 5, we will create an edge where end vertex will be 2, weight will be 5, and we will store that in that array. So this notation right now we will not use today, but this link is there in this date and class for you to refer. And here we have given code also how do you create a graph with which represents even weighted, unweighted graphs, directed, undirected graphs. So here if you see, we are using a pair, first vertex, second vertex, sorry, first and second, where you can say first can represent the first vertex, the endpoint vertex, and second can represent the weight. Tomorrow we can add third thing also. If one edge is representing 3 things, 4 things, we can always add more fields to this class, right? Okay, so here we have language code available for all the languages, and this code that we have written, it is generic. It can work for weighted, unweighted, directed, undirected. All the graphs can be represented using this. But today we will start from basics so that we are able to grasp graph and we are able to code it perfectly. 1 is connected to 2 with a weight of 5 here. Yeah, let's see. If 1 is connected to 2 via distance of 5, connected to 3 via distance of 4, and let's say they are connected with the distance of 1, right? So 1 will have a list, because see, this thing that we are seeing is an array. There is no change in that. Go back to the notation. G is still an array. In every location of array, there is a list, but each element of a list is a edge, right? So let's see now. We are talking about 1 is connected to 2 via 5. So what we are doing in this array location, we are storing a list. Initially list is empty. First value in the list that we are storing, that's a complex data type, and that is saying 2, 5, where 2 is the vertex and 5 is the weight between edge 1 to 2. 5 is the weight of. Now let's complete it so that we are able to visualize it clearly. What is the next thing? 1 is also connected to 3 via 4. So 3, 4. So you are first saying this is a vertex, this is the weight, vertex, weight. So this is representing an edge now, correct? So then we are able to visualize the entire thing. So this will make it clear. So keep in mind that first we get the index access there, then we get access to the list. If that list is of edges, we know we have to get end vertex and end weight. That's how we deal with it. Right? So it is data structure of data structure. That's where the confusion comes at times when we are coding this. In place of array, if I use map also, then also it works the same way. In map, go to that index, get the value will be a list, and play with the list, right? So first problem that we are going to do on mentor pick is read and print the graph, right? So what this is saying is, you are given some input format is described here. We have left the, sorry, this is filled code. Only C# will have the filled code, and ideally I'll say C# folks also delete it and start from scratch. What we are doing, we are reading this input, we are creating a graph, and here if you see number of vertices in the graph is 10 to the power 4. Usually up to 10 to the power 3 vertices, we can always go with adjacency list representation. But beyond 10 to the power 3, beyond 1000 vertices, the matrix, if we declare 10 to the power 4 by 10 to the power 4, we may get MLE, memory limit exceeded. So for bigger notations, we always go with bigger graphs, we always go with adjacency list representation. And adjacency list representation, we can stick to 2, which is map of int, comma, vector of int in C++. This will represent our graph. And in Java, it will be map of integer, comma, list of integer. This is little complex. The simplified version of this that we will be using is vector of int G array and list of integer. That is what we talked about, G array. Right, so we will go and create an array like this with the maximum number of vertices that is given, and that is how we will create our graph. So we are clear. We have to read number of vertices, number of edges, declare the graph, and fill the list of the graph, and then we just have to print it out. So just read the problem statement, give it a try, then we will code together also so that we are clear. After this, we will understand the traversals, and then we will do some problems and graphs.
This conference will now be recorded.
Sorry?
So I'm saying we will talk about the implementation. This is the first problem we are doing, so we will talk about the concepts that we are applying in this.
This is read and print graph, right?
Yeah, read and print graph of data.
Okay. Okay.
Based on problem statement, if you look at input format is clear to everyone. After reading the input format, we have to create a graph with adjacency list. An adjacency list, we said we will use an array, right? So what we can do, first line when we are reading 2 integers. If both integers are -1, -1, we are done. That is what the input is saying, that whenever you see -1, -1, that's the end line of input. Otherwise, read it and proceed. So in Java, how do we read the first line? I can say this is number of vertices, sc dot next int, number of edges, sc dot next int. This is the first line of every test case, right? And I have to run it for all the test cases. So can we say this is while true? There is some sort of loop that we have to run. And immediately after we read the first two inputs, if nv is equal to -1 and ne is equal to -1, break. So we have read number of vertices, number of edges for the first line. Now with the help of this, how can we declare a graph? Yeah, what will the declaration of graph look like? Yeah, Mustafa. We know number of vertices, we know number of edges. So how do we declare graph here? List of integer g of, if it is C++, we will write directly nv plus 1. Why plus 1? Vertices are starting from 1, so we want one additional index to be there. In Java, we write it on the right side. We say new list of integer of how many elements? nv plus 1. So this is Java notation. C++, we can directly write vector of int of g nv plus 1. That is good enough for C++. So this way we are just creating an array which will have the list for every vertex. So far this is clear?
Now, 1 second. Let us see if it is clear or not. If I try to print the G0, 0th index of this, what I will get? G0. You will get list of integer. Did somebody stored it there? Empty list? No. It will be null. Isn't it? Currently we created, it's just a reference. This reference is not pointing to any object. U is for array. So we will explain, but that's what we wanted to clear, right?
So we just created an array where we said each array element can store an object, right?
Can we say store a
Reference to an object. Yeah.
reference to an-
Imagine if you declare something like this. Let's say you have a class in Java, list of integer al. What is the value al has right now? It is null. Everyone agrees? Same way, if I declare another object, let's say there is some inbuilt class student s. If I don't put new, what will it create? That means it will be null, right? That means just when we declare an object, by default it is not initialized. Here there are two things, whatever we are declaring. We are creating an array. Array is instantiating using this, but objects in the array are not. So what it is doing is, it's creating an array where 0 index is null because we have not inserted anything. First index is null, second is null. Right now they are null. We have to create an empty list here to which we can add. This makes sense? So what we will do after this, we will also say, let me go and add an empty list so that we can append to it. So we will say for I is equal to 1, I less than nv, I plus plus, g of I is equal to new array list of integer. Am I doing things correct? That every array list I am creating as an empty array list. Is that clear?
In the if condition, why have we taken and instead of or? Because if nv is -1 and na is not -1, that doesn't make sense, right?
Yeah. Yes, good catch. So if you come here, Prakash, read the problem statement. What does it say?
Okay.
Here we are just following what problem statement is describing. It's not a logical thing
Okay.
that we are assuming that if anything is -1, it is as per the description. Okay, this code has a
Okay.
bug. It has a problem. Can you identify what mistake I have made in writing this loop? I less than equal to NV, right? That's a common mistake we do when we play with 0 index or 1 index. So this should be. Now, if you are coding in C++, ideally you can go ahead and say g of I in this loop is equal to vector of int blank. But in C++, the vectors are initialized by default. Even if we do not write this loop for C++, we should be good. But for Java, for C#, explicitly we have to initialize. Correct? And because in C++, the default constructor is called automatically. So this is clear why we are initializing this. Now we first created an array. In array we added empty list. So that is the state we are in. Now we can start adding to that list. So what is the next line we read from input? We read NV and NE. We created a graph. What is next line representing? Next, how many lines we have to read? Yeah, NE. Because it said first we will give you number of vertices, then we will give you number of edges. After that, next 13 lines are giving you those relationships, which vertex is connected to which other vertex. And this graph that we are creating, this is what type of graph? This is undirected. That means if there is an edge between U and V, there will be edge between V and U also. Correct? Same way, for this is undirected. For unweighted, our notation has already chosen it to be unweighted graph. So here we go ahead and say for int I is equal to 1, I less than equal to any I plus plus, we go ahead and we read U and V. U is the first vertex, sc dot next int, and V is the second vertex, sc dot next int. And somehow we have to insert vertex U and V in the graph. This line I am not writing. Fill insert edge in G. This is what you need to do. And after that, you will be print the graph in desired format. So this is what essentially they are doing. Right now, you should be able to figure out what lines do I write so that every edge gets inserted, and how do I go and print the graph in the desired format that problem statement is describing. So just go fill this code, submit it. If you get stuck, let me know. But this notation is something we need to get comfortable with.
This conference will now be recorded.
What will be wrong if I declare my graph over here? We don't know the size. Okay, I go with max size. Now it should be fine. Huh?
Sandeep, the screen is not being updated.
Screen is
I'm
not
not
being
sure. I
updated.
can, yeah, I can
Oh,
see
you did
you in
not
real
see.
time, but
Okay, I'll do one thing. I'll just switch off. I think it got switched to the Wi-Fi connection. Yeah, it's possible. I'll see, Prakash. I think.
okay.
Yes. Absolutely, yes. If we are declaring graph here, that means it becomes common graph for every test case. Prakash, is this line visible now? Line number 8, where I
Yes.
yeah. So this is what I moved. We are saying if we declare the graph outside of while loop, that means for every test case we are going to use same thing. In C++, we can do this globally also. or we can put this in the first line of the main also. But then this will, for every test case, this will interfere. But inside that, if you see, since we are initializing, every graph we are initializing with new array list, and we are going to deal only till then, it should be fine. But if you move this also here, it will be a disaster. So make sure when you are writing multi-test case kind of programs, for every test case we are creating a new graph. That's the guideline. So we are going back to the original thing. So anyone who has declared the graph, make sure your graph is declared inside the loop. For every test case we get a new graph.
In general, it is now suggested that you declare a variable only when you require it, right? Old C programs, we used to declare everything in front, right? And then we used to write code, even for loop int ij. Now they have changed this guideline, right? Whenever you require something, just before that you declare. That way we can stop making these type of mistakes.
And people who code in CC++, a very common mistake that happens is this. We read number of vertices, number of edges. What is the mistake in this line? Ampersand missing. Yeah, so just be aware of that, so that we are dealing actually with the graph issues, not with the basic issues. Okay, now tell me, how do we insert edge in the graph? We are inserting an edge from U to V.
G of u dot add v.
G of U, if we are doing, what is this going to give us? This is going to give us a list, because this is G is an array of lists. So this is the list of U. Then we'll add V to that. This will work in C# and Java also. Next line you will say G of V dot add U. If you want to try to visualize what exactly we are doing, we had an array. This array just had an empty list so far. There is no list here, no list here, no list here. We say insert 1 to 2. So we go to 1 position. Here we get a list of all the vertices which are connected to 1. We are putting 2 in that list, and we go to 2 and we put 1 in this list. So this is like in array, go to location U, you get a list back. In that list you add. If it was C++ code, they would have said G of U. The function in C++ is not add, this is push underscore back. G of U push back V, and same way G of V push back U. And Arun, I guess there will be one more difference between Java and C#. The function name will be capital. In Java, all function names start with small letter. C# all start with capital letter. So everyone agrees these two lines will add a vertex to a list. Bhuvan, is it clear? Huh? Okay. So if we want to create one vector, how do we declare one vector? Vector of int v. Now I say give me 10 vectors. If you declare one integer, you declare like this. I say give me 10 integers as an array. So what do you do? Int. How do you declare an array of 10 integers? Int a10. So this is int one integer, this is array of 10 integers. If this is one vector, what will be array of 10 vectors? Can we correlate this one and understand? This is one vector, this is array of 10 vectors. This is one integer, this is array of 10 integers. This exactly is what we did. We wanted array of nv integers. So array of nv lists. So that is what we did here. We created a vector of int g of nv plus 1 because it is one index based. Now what does it say desired format? Yeah, what do we have to print now? Graph creation clear to everyone? What we have to print, it says for every vertex, print that vertex number, space, colon, space, adjacent vertices in the sorted order. How do we do that? How do I print every vertex? Look from 1 I less than equal to nb I plus plus. Inside this loop, what do I do? First print this vertex, printf percent %d.
But it's not given anywhere that vertices are natural numbers in some order.
Okay.
Consecutive natural numbers.
Vertices that are given to us might not be in that order. Can we sort and print?
Yeah, but if you are looking over I2 and
What does it say here? Vertex number are guaranteed to be 1 to 10 to the power 4. They will be consecutive, that is given. And if you see sample output also, it is given.
what if it's not consecutive?
If it is not consecutive, then problem statement will define some order in which you print. It may say that give me all of them in sorted order. Right? So here it is in line with what we need. So we print this. After that, what should we do? All the adjacent vertices we have to print, and we have to print them in sorted order. So first let's get what are the adjacent vertices of I. Vector of int adjacent are g of I. Here it will be list of integers. Sorry, Java code. So we are getting a list of integer. Now this list has to be sorted and printed. How do we sort this list? ADJ. If it was C++ code, we would have said, here we would have said vector of int ADJ is equal to g of I, and here we would have said sort ADJ dot begin ADJ dot end. That's the way we sort there. And once it is sorted, it's a matter of just printing a list. That's it. So how do I print this list now? For j is equal to 0. We have a list, but this list we want to print, right? ADJ. J less than ADJ dot size j plus plus. System dot out dot printf percent d. What do I print? ADJ dot get of I. Yeah, ADJ of get of j. In C++, if it is vector, we could have directly done ADJ of j. So everyone clear what we are doing, right? And it is just making us comfortable with the graph notation, how it is stored, how we are using adjacent vertices.
Sandeep, I am getting an error for line number 16. It says generic array creation.
Line number 16. Coding in
Yes.
Java only, right?
Yeah.
Okay, so can we delete integer and try once?
I did that as well. It is still giving compilation error on that particular line only.
Huh? Oh, angular places we have to remove. I'm not sure. So this is what Satyam is suggesting. Yeah, if we remove angular brackets, then it should be fine.
Can you please ask him why he asked to do that? I mean,
Okay, actually here list is the list that we are using. It's an index. Ideally, here if we write array list, then it should be fine. Because this is a what do you say? List is an interface in Java, not a a class.
Yeah.
So we never do new on an interface.
Okay.
Yeah, so it's Java syntax. So just stick to like new list and don't put angle brackets, and it should be fine. You're getting error in C++. Sure, we'll take a look at it. Submissions are not working. It is working. Okay, maybe there is some issue in this. Huh? Yeah. Sorry. Yeah, that should also be fine. So the error it is giving, it is saying has no member named pushback. So where is your map declared? This is your map. If you take a map, why do you need this array notation then? You submitted? Worked? Okay. Yeah. If you use map, then it's no more array. So just yeah, if you are submitting, it is not working, let us know. We can open your code, look at it, and fix it.
Sandeep, if it is not given in the question that the graph cannot be modified, then is it okay not to use that adjacent list at the end and just use sort on G of I only?
How do you sort on G of I? G is an array of lists.
Yeah, so G of I will give me the list, right, at ith
Yeah,
index?
yeah. Oh, you are saying rather than storing it in ADJ and then taking, right?
Yeah,
You could have directly written G of I here. It's just for
yeah,
explanation. I have split it into 2 lines.
yeah,
But
okay.
modifying the adjacency list, even if you store it in ADJ and sorts, you are still modifying the graph.
Yeah.
Okay, everyone done? Anyone for whom this is not working? Yes, I
Me.
can. So that was the only issue. Yeah, Om, work for you? Srinivas, Udbhav done with this? Aviram, Samir, working? Okay. Online guys? Sure. Yeah, for anyone, if this is not working, let us know so that when we move ahead, we are clear about the syntax. That should also be fine. You're using C++, right? So if you're using vector of vector, okay, let's see. You used vector of vector. If you typically do that, there are some issues that happen. So usually I'll say initialize it with nv, comma, vector of int, so that you are saying that this notation is, it says how many values you need and what are the default values for each. So we are creating empty vectors. Is vector a vector notation? You took v, okay. And you are going with 0 index based or 1 index based. So you should do v plus 1. Let's try now. So it is like we are initializing all the vectors empty, but even now it is failing. Let's see if there is any other issue. You took v and e, v1, v2. In v1 pushback v2, again v1 pushback v2. Okay, that's fine. We will just, yeah, v2 pushback v1. Okay, then you are going with 1 to v, all the vertices. You're printing I, you're getting that, sorting it and printing it again. Yeah, code wise it looks fine now. Let me try once again. But here, where are you reading, Amit? Where did you read V before you put this line? What is the value of V here? You're using a garbage value, that is what is causing problem. So after reading only we should create. So let's cut it here and put in fact after -1 because here also you will get into trouble. Yeah. Okay, now output is coming but new line is missing. So issue was that you were using a garbage value of V. Okay, sure. So Bhuvan, it is making sense? Coding wise it may be hard right now for you to pick. That's fine. Sure. Online guys, anyone who needs help with this problem?
So once can you check my code?
Sure, Yojit.
Sandeep, only because this question said that the graph is unidirectional, therefore we added those two lines, right? G of u dot add v and g of v dot add u.
That's right, absolutely.
Okay.
If it was a directed graph, we would have inserted only u to v, not the otherwise.
Okay.
Sandeep,
Yeah, Lavakumar.
can you just explain why what happens when we add g of u dot add v and g of v dot add u?
Sure. Okay, then break. You're initializing array list. This you're reading, creating. Okay, here you got length. You are printing I. If length is not 0, you are sorting 0 to length. G of I dot get of j. Okay. As code wise, do you see any mistake in this? So he's getting error in line number 8. He's getting error in line 27. Line 27 is this. Yojit, this line there is a mistake. Can you catch that? Line 26.
It should be less than equal to n of v, nv, right? nv
Yeah,
plus
Yojit, it should be
1.
NV.
nv, yeah.
Got it.
Yeah. So because vertices in the first graph were 7 and edges were 8, in 8 you are getting out of bound exception. Okay, same way Mustafa's code. What, you figured out the mistake? Okay. Yeah, so in between, Lavkumar asked like why we are doing u of v, v of u. So here it is undirected graph. If one is connected to 2, one's list will have 2, two's list will also have 1. Lavkumar, is that clear or not? Undirected graph. One is friend with 2, 2 is friend with 1.
Yes, Sandeep.
So this is an array. In that array we are pointing to a list. In that list, in 1 we are putting 2, in 2 we are putting 1. That's the reason we are doing it.
Okay. Okay, because this is undirected graph.
Because this is undirected. That's true. If it was a directed graph, we would have inserted only one edge.
Okay. Sandeep, can we use a map of integer comma list here also and try to solve
Yes.
this problem?
Yes. Ideally, for graph, you can use 3 notations. We said map int, list of int. This is one. Second is you can use list of list. And we used simplified one, array of list. Anything is fine.
Okay.
Sandeep, what will be the difference between the last two, using map and using list?
Okay, if you use a map, even if your graph is, let's say if your graph is of characters, it doesn't have vertices which are having number from 1 to, if this has any alphabets, random alphabets, it can have Z also, then this notation will not work because your vertices are not in an order. Right, Prakash?
Yes, but what will be the difference if we use map notation and we use the second list notation, the one written in line 65? I mean, any benefits of one over the other or any differences?
Okay, so you are asking very basic question, difference between list and map.
No,
Ideally,
no,
by now we should know that answer.
no. I'm not asking that. I'm asking in graph sense. Is there any other difference other than
Okay.
the list and map
No,
difference of
no, code wise, syntax wise, there is no difference because the way you get an item from a map, the way you get an item from list, code wise, there is no difference.
Okay,
Yeah.
okay, got it.
The only thing we are talking, only reason we are giving you three notation is because sometimes when you are creating graph with random vertices, you know that this notation and this notation will not work because here we rely on the vertices are numbered from 0 to n or 1 to n. Right, then this notation comes in handy. Code wise, all three will have a slight difference in coding. Okay. So first problem, can I assume everyone is done with? Now let's talk about a good concept in graph. Now the problem we do, graph will be mostly given to you and you have to act on that. This problem is of a directed graph, has a lot of practical applications, and we want to think of some logic of doing it. For now, okay, graph wise, all the graph problems we are doing, we will do with vertices in mind that they are numbered from either 1 to n or 0 to n, and we should be comfortable with both. So let's say there is a directed graph given, and what this directed graph is telling us is each node is representing some event, or you can say some step for an event. Imagine if you are arranging a birthday party, you do some work items, right? If you are arranging for a birthday party, you have to order cake, you have to get balloons. So all these tasks that you have to do, those tasks will have some order in which you will do them. This is representing you will do first. After first is done, only then you can do three. This is the ordering we are defining. Once you are done with one, only then you can do two. So this is, edges are representing dependencies between them. Now, if this kind of graph is given to you, the question that is asked is, give us the order in which you should do all these work items so that that order takes care of proper dependencies. 5 is? No, 5 will be last in the output. 5 cannot be done. Order is like, this is dependency. So it says 3 is dependent on 1. After 1 only you can do 3. After 3 only you can do 4, like that. Oh, okay. Oh yeah, you tried in the other way. For now you can say these arrows are telling what item you can do after this. So what is the order? Looking manually at it, first you do
1,
1,
2, 3, 4, 5.
2, 1 ke baad you cannot do 3. 3 cannot be done until unless 2 is done. There is this line also, right? So 1, 2, after 1 you could have gone to 3 also, but you are saying no, after 1 you cannot do 3 because 3 has one more dependency. Okay, then after 3 can we do 5? No. So this order we want to produce, given any graph, this order if you list, this is called topological sort of a graph. In real world, have you used systems like Maven? Java people should be aware of Maven.
Yes.
Makefile in C++, MS Build for C# folks. These build systems, what they do, when you have bigger projects, when you have source code files, you write a class, another file uses that class, or you write function in one file, another file is using that. So can we say files have dependencies on each other? So we say you can compile file 3 only when 1 and 2 are compiled. So all these build system come up with an order in which they should be compiled so that your output should come properly. right? These build systems use this topological sort. Clear? So application wise we know. So now the question is, if somebody says we are giving you a graph in some format, let's say graph is given to you of sort, and you are given a graph vector of int g. This is the array that is representing the graph. C++ variant, Java variant is list of integer. So if your graph is given in this format, we say print the topological sort of a graph. You have to come up with some strategy and go ahead and do it.
So one question here, is the topological graph, topological sort, I mean, is only possible on graphs where the dependencies or something like that is given some order
Yes,
of some kind.
that's right.
So
So
can it
topological
not be done on undirected graph?
no, it cannot be done on undirected graphs because in undirected you don't know the order.
Okay.
Yeah, and topological sort is done on directed acyclic graph. What happens if there is a cycle?
Deadlock.
After 1 do 5, sorry, after 1 do 6, after 6 do 1. So topological sort is also used in detecting whether graph has a cycle or not. That's another interview question that gets asked. Given a graph, tell if it has a cycle or not. So first we are seeing, can we think of a way to come up with a topological sort? So everyone said, looking at this graph, choose one. What was the reason behind saying that?
Because there are no incoming edges on one.
There are no incoming edges. So okay, incoming edges became the criteria. For every vertex, can we write how many incoming edges they have? How many incoming edges one had? How many incoming? How many 3 have? How many 4 has? How many 5 has? Number of incoming edges of any vertex in a graph is called in degree of the vertex. First time when we introduced the graphs, the first question was for every vertex calculate its in degree as well as out degree. That was the problem statement. Right? So if you have not done that, today we will cover that also, because today we are focusing on coding graphs, because usually the topic seems heavy, but ideally it's just a matter of syntax practice. Otherwise, this is graph problems are very easy to nail, and they give you an edge. If in interview somebody asks you graph problems, you can impress easily if you are able to solve that problem rather than giving up on that. Right? Okay. So first thing we said is, in order to do this topological sort, let me go with your approach. Let's take an array where I'm just calculating in degree of every vertex. So what is in degree of 1? We said 0. In degree of 2 is 1. So this is in degree array. Do all of us feel comfortable after printing the graph that we just now did? Using the same strategy, can you fill the in degree array of all the vertices? How? What changes will in graph printing so that
What we can do is, while we are traversing through the array of lists,
yeah,
uh, uh, let's say we have a edge from 2 to 3, so we will
correct,
add an in degree to the 3, that the edge from 2 will act as incoming edge for 3.
correct. So here if we take an in degree array, for every vertex we are storing the in degree. In this loop, where can we put a line where in degree of a vertex is increasing by 1? What is I here? Oh, this was the mistake I did. I here is the vertex which is the starting vertex. Here get of j is a vertex that we are printing, it is.
Each vertex
It's a vertex in adjacency list. What it is conveying is there is an edge coming from the vertex I to current vertex. Here we can update in degree of some vertex. What will that vertex be?
adj.getj.
J is the index in the J is the index in the list. J will always be 0, 1, 2, 3.
degree of
In degree of no. I is the vertex from which the edge is starting. Think about it. Let's see.
adj.getj.
From 1, if there are edges to 2, 3. From 3, there are edges to 1. From 2, there is edge to 3, 1. Now tell me, in this loop, I is this. From 1 you are starting. Index 0, index 1 in the list. This is J. This is I. adj.getOff. J will give you that particular vertex because that is stored in the list. You say for 2, since we have seen 2 in the right side in the adjacency list, we say 2 has one edge on it now. So can I say in degree of adjacency list dot get of j plus plus, assuming that I have initialized in degree with 0. This helps me calculate in degree of all the vertices. Now if we give you some practice problem, calculate in degree of any vertex, out degree of any vertex. If we just give you problem of finding in degree of one vertex, can we do that? Here we are calculating in degree of all the vertices using a loop. For one vertex also we can do that.
Yes.
For in degree of one vertex, do we need a nested loop or not?
You can directly access the.
Yes, we do.
We need. If you directly access, you can get outgoing edges. But in edges, you only get by traversing the list. For in degree, you need to look at all the adjacency lists. You cannot say just by the array. Correct? You still need it. So it's always better we calculate in degree of everything in one shot. Now you keep asking, we'll keep returning the value from this array, right? So in degree calculation, we are clear, right? Okay, so first step we are doing is we calculated in degree of every vertex. 3 has in degree of 2, 4 has in degree of 1.
But Sandeep, for topological sort, only in degrees won't help, right? We need the node from where there is an incoming edge,
Okay.
won't
But
we?
when, yeah, so we are just trying to formalize when people said 1 is the first vertex, we are going ahead
Okay.
with that. So we just
Okay.
calculated degree of all because for 1 also we would have written nested loop, correct?
Yes.
So after you gave 1 as output from this, you said 1 has in degree of 0. Let's search in this array which vertex has in degree of 0. You searched and you said 1. Let's go and print 1 so that in computer when we write the program, it is easy for us to write. Now once 1 has been printed, can we say the dependency of 3 and 2 is done? They are ready as next candidate if their in degree has become 0. After 1 is over, can we say 2 can be done now? Correct? When 1 is done, what we do after 1 is done, all the edges that were going out of 1, there are 2 edges going to 2, going to 3. Let's go to 2 and decrement it's in degree. Let's go to 3 and decrement it's in degree because 1 is done. Is this clear? Every time you keep finding the next vertex whose in degree is 0 because he is the next candidate for topological sort. And once that item is done, once that item is printed, you say all the edges that are going out of him, let's decrement the in degree of other vertices. Now if you see next vertex candidate is 2 whose in degree is 0, but 1 is also having in degree of 0.
So once the node is printed, we should decrement it to -1, so that
Yeah,
it is.
let's make it -1 so that we are not changing finding that. We are finding only the next vertex whose in degree is positive as well as 0. Right? So we found this vertex. For 2, we printed 2. So first we printed 1, now we printed 2. After printing 2, look at all the edges going out of 2, which we can find from the graph, and decrement their in degrees. So whose in degree will decrement now? 3's, and it will become 0. And make 2's in degree -1. So this -1 is helping us know that one vertex is over and it is done. It's like visited. Now you print 3, then you print 4, then you print 5. Will this approach work?
Yes.
If you remove an edge between 2 and 3, yes. Good question. So in system, if we formalize the steps that we discussed, can somebody tell what is the first step we did? Given a graph, we want to do so that we can evaluate the approach. First step was
Calculate in degrees.
clear in degree array every vertex. Okay. Now you are doing something. What was our first selection? Now we don't know which vertices are there, right? We are just okay. You are saying find vertex with in degree 0. This is what you are trying to find. Let's say we will do it separately. We got that vertex. Okay, done. Then what do? You got this vertex. What should you do with this vertex now? Print it, because this vertex deserves to be printed in topological sorted order. Okay.
Then we traverse through the list of its edges and decrement the in degrees for all those vertices.
Make its in degree -1. Yeah, what Prakash is saying is go to all adjacent vertices of V and decrement their in degrees. But this we did once. This should keep on happening. How many times it should keep on happening?
Vertices number of times.
Vertices number of times?
Until all degrees -1.
Minus.
So this all should happen in a loop. Everyone is agreeing to this? Yeah. Yeah. 3's in degree will still be 1. Sorry, 3's in degree was 2 earlier. Now it is 1. You clearly know 3 will not be selected. So this function that we are calling, this will go over your in degree array and find a vertex whose in degree is 0. Right? Then you find the right candidate. This will have a loop again. This is a function, if you see.
Sandeep, in the graph, if the edge between 2 and 3 was not there, so the in degrees for 2 and 3 would be 0 at the same time. So how do we decide
Absolutely.
which one to go for next?
Good catch. So this is a good observation that Prakash has made. Imagine if our graph is this. So who will be our first candidate for topological sort? It could be 1 or it could be 2. So topological sort of a graph can be multiple also. It's possible. So that's the question Prakash is raising. In that case, which topological sort we go ahead and do? So ideally we can go with any, or complex problems will say give me all topological sorts of this graph which are possible. So topological sorts are multiple. So today what we are doing, we want to go ahead with 1. Later on, if you want to go ahead with all, then it becomes a backtracking problem. The first vertex which has 0 in degree, let's go ahead and print that topological sort, come back, find the next vertex which has in degree 0 and go ahead. So every step we have multiple paths. So yeah, good observation, Prakash. So this is clear, topological sort concept?
Can we please discuss the complexity once of this sort?
Yes, that's what I'm coming to now.
Okay.
Yeah, we will talk about all these things step by step because topological sort has a lot of things related to it. That's what we are getting into now. So first let's talk about what is the time complexity of this overall thing. Let's say graph is given to us. Declaring in degree array is just a declaration. Calculating in degree of every vertex. What will be the time complexity of calculating in degree of every vertex?
Order of vertices.
Only order of vertices?
No, order of vertices into edges. V into E.
Two edges. Okay, whenever we represent time complexity for graphs, we take into account two things: number of vertices, number of edges. Right? So we have to keep both of them into picture, and then we have to express. Earlier in array we used to say order of n square. Here we will represent with V and E. Now for the time being, if I say for every vertex for calculating in degree, there was an outer loop. For every vertex, we were covering the edges of that vertex. If overall edges in the graph are E, can we say there will be sum of first vertex edges, second vertex edges, third vertex edges? Can I say that? And last vertex edges. Right? Or another way of looking at it is, for every vertex I'm covering its edges. For first vertex I covered E1 edges. For second vertex I covered E2 edges. For third vertex that and EV. Overall, the nested while loop is running E times. I'm covering outer loop as well as inner loop. Do you agree with that? Prakash, can we say it is E times?
Yeah, because for every vertices, if we calculate overall, it would be E times. Yes.
So we can say it is E times, but keep one more thing in mind. If I give you a graph where I put 10 vertices and no edges, there are 10 vertices but no edges in the graph. Now how many times our nested loop will run?
Nested loop 0 times.
No, overall. Nested when I say outer as well as inner.
Okay, 10
V
times.
times. Correct? So V times it will run. So we always say, we never say it's only E. Ideally, we know E would have covered if all the vertices were connected, because we are running it edges number of time. But we typically express it this so that we are not missing out the case when edges are not there. Then at least we are going V times. So it's expressed as this is E plus V. That's the time complexity of this. Make sense? For each vertex, you are covering that vertex edges. For another vertex, that edges. So see, first vertex you covered E1 edges, second vertex E2 edges. If they all had edges, it would have been sum of all these edges. That would have been the time complexity, considering outer as well as inner loop. Do you agree with that or not? So that's how we came to the conclusion that E is the time complexity anyways, but that was assuming that all vertices are connected. If they are not connected, then V factor is also there. So let's express as E plus V so that we cover both the sides. So typically in graph, we represent it in form of E and V. We say if you are printing the graph overall, the complexity is E plus V. This is clear? Okay, so first step we are saying this is V plus E, where we are calculating the in degree. Now, how many steps will this take? This is a separate function. Every time we call that function, every time we call
Can we maintain a min heap for this?
yes, good. We are coming there, Prakash. Yeah. Every time V steps. This while loop we are running how many times? V times. Overall, think of it. This loop will run V times because every time one vertex is going out. Or we can say this loop can break earlier also if no such vertex found. If I give you a graph, a bad graph like this, 1, 2, 3, and this. How many in degrees of 1? In degree of 2? 1 has 1, 2 has 1, 3 has 1. Let's start topological sort. Which vertex we pick? Can't pick because 1 doesn't have in degree of 0. Huh?
Direct acyclic.
Yeah, okay, in today's context that way. But if I give you a cyclic graph, in this case we will not be able to proceed. So ideally we should have a way to detect. If we are calling a function and say give me a vertex whose degree is 0, and if it doesn't find, it says none of them has 0, we should have a way to detect, and we say a break. If we have not printed n vertices in this loop, This is actually the cycle detection algorithm. What it says, create the in-degree array, call a function, ask him what is the next vertex with in-degree 0, get that, print that vertex. If this loop is running v times, we say graph doesn't have cycle. But if this loop is running less than v times, we say somewhere graph had cycle. Ideally, this loop should print all the vertices of the graph. If it does not print all the vertices of the graph, somewhere it finds this kind of situation, it will never get a vertex and it will break out from the loop, right? So we will come to that cycle detection once again, but for now, let's say we are going ahead with this, and in today's context, we said we are giving a valid graph, which is directed acyclic graph. Then, this will take v time, because what we are doing, we are looping over the entire array. This is something we will optimize. This loop will take v times. So overall, this is running v times. This is a v step process. Printing one vertex is order of 1. Make its in degree minus 1. Current vertex in degree minus 1 is order of 1. Go to all adjacent vertices of v and make their in degree, decrement their in degree. For that vertex edges. Again, here and here, if you take, it is same way like we analyzed previously. Can I say this is v plus e? Because for every vertex its edges, every vertex its edges, it is overall v plus e for this and this. For this, it is v extra, so it is say v into v plus e. Clear? Inner part is v plus e. No, inner part is not v plus e, because inner part it is v here. Here it is e of that vertex. It is e1 of first vertex, then e2 of second vertex. For every vertex, if one vertex has 3 edges, we will go 3 times. If it has 5 edges, we will go 5 times. Yeah. It is not e times. For one vertex, it is not e times. For one vertex, it may be e1 times, even our edges. For another vertex, it can be e2 times. So what we are doing for this and this combined together, we are writing e plus v. That's what we did previously also. But for this separate thing that we are running, we can say it is v square. Is it fair? Now outer and inner combined, I say e plus v. Yeah, that is what it will be. It accounts for both. And since we are doing outer loop v times this, we are doing every time v, this is v square. Is this clear? Yeah, here this is little tricky to understand, because inside this loop is controlled by how many edges each vertex has. That's why we always say if outer loop is v times, inner loop is number of edges for that vertex, we always express these two things combined as e plus. Is it making sense? That's right.
So Sandeep, overall complexity would be O of v plus e for step 2, O of v square for step 3, and O of v plus e for step 6.
Yes.
Right. So
So
can
v
we say that v square would always be greater than e plus v?
Okay, can we say v plus will be always greater than e? Is it fair to say?
Asymptotically, yes, we can say.
Every vertex can be connected to every other vertex. The maximum edges in a graph can be how much? If 1, 2, 3 are the vertices, what is the maximum number of edges that this graph can have?
3.
No.
5, 6.
6. Now?
N factorial edges, maybe?
No, it is not n factorial. Sigma n minus 1. Can we say sigma n minus 1? Think of it. 1 is connected to how many vertices?
Okay, n into n plus 1.
V. One is
Sigma
connected to n minus v minus 1 vertices, one is connected to. Now 1, 2 is already covered. 2 is connected to how many other vertices? Ideally 2 is also connected to v minus 1 vertices. If it is an undirected graph, we see it the other way also. But you can say v minus 2, v minus 3, all right. Yeah, so those many edges. Worst case, you can say it will have v square edges, but we are assuming that they cannot have self loop. If I start putting self loops, then it is infinite. One or parallel edges. 5 and 1 can be connected through multiple channels. Then also more edges can be there. In directed also you can have 2 edges, right? So number of edges can bloat up if you have unrestricted graph. Parallel edges, self loops, all that are there, right? So in this, the challenge is we want to cut down on this time. So we will see that this topological sort approach that we took, this can be solved again using 2 ways, BFS way and DFS way. This way that we did, we can ideally optimize this finding using BFS, and there is one more algorithm to print topologicals or DFS. So next what we are going to go is we are going to start from the previous class 3 problems. Previous class 3 problems we said in degree out degree calculation, BFS and DFS, because we do not want to leave any scope of people not practicing at home. So we want to cover that. So we will go back to the old class, cover those 3 problems, come back to today's class, cover topological sort in both ways, BFS and DFS way. But the idea that you saw, it's clear, right? If we have to solve this problem in inefficient way, we know there is a solution. We can code it. It's just a matter of finding the syntax approach, we got it. So we need to find the optimized way of solving it. That is what we will be coding, not this, right? Before going for a break, one interview question we'll talk about. You are given few words. You have to take that, I believe, the problem statement directly, alien dictionary. Yeah, so this is a problem statement. What it says is there are few words which are not according to English dictionary. That means the language has been changed and these words have been given to us from another language where alphabet's order has changed. In our alphabet ordering, we know A comes before B, C. This is the alphabetical order, right? What this problem is saying is this order has been changed in alien language. What help we are given is we are given few words here. These words are in dictionary order of that language. If it was our English dictionary, out of these words, which would have come first? A, B, C, D. But in their language, BAA is before A, B, C, D in their dictionary. So what conclusion can we draw from BAA and A, B, C, D? If these are
the order would be B, A, C, D in their language.
empty string will not be there in this. If two words are given, what conclusion are you able to draw? You have to tell the order of alphabets in their language.
B, A, C, D
Let
will
us
be
say
the order.
A comes after B in their language. Can we say that between these two words? Because word starting with B is first, word starting with A is second. So we say, hey, B comes before A. This is the conclusion so far we are drawing. From these two words, can we draw any other conclusion?
But seeing the second letter, A is coming before.
Seeing the second, imagine in our dictionary, apple comes before cat. We define A and C's order. Other words will not matter. If we find first mismatching character, after that, you cannot decide order based on that. Can we say that? Yeah. So two words are giving us one order. That is what we concluded from them. Let's compare these two and get some order.
B comes before.
B comes before A? No.
D
comes
before A.
before A. So D is before A. This is clear? Because here we said A is matching. leave it. B is matching, leave it. C is matching, leave it. Oh, D has come before A, so in dictionary, D alphabets word is coming before, that means D is before A. Now compare these two, and C comes after. Compare these two. B comes after.
B comes after.
Right. So you go over the list of strings, define this order. Can we build a map which stores this order? Is that map a graph? Okay, now we want to give the words in dictionary order, the alphabets of that alien dictionary. What algorithm will solve this?
Top sort.
Correct. No, it's not guaranteed to be a single line. Sometimes you can be given dependencies like this. Here you saw BA, BD dependency was coming. I can also give you a word which has this relationship also. D comes before C. Can also give you a word which comes this. If I give you more words, can I give words by making this relationship? Uh-huh. No longer needed. Yeah, that's correct. No, depends. We are saying first build their dependency relationship. You are actually building a graph. Correct? After you have built a graph, what order are we looking for as an answer here? Topological sort, right? This problem is topological sort problem. You just build a graph and give topological sort, problem is solved. Right? Huh? Yeah, look for first vertex which is inbound 0. Right? So this is like, if you are given this kind of problem in an interview that some words are given, one word comes before other. So first indication is, okay, words are having a relationship between them. This comes before, this comes after. So there is a relationship. Before, after, it is telling this is some sort of directed graph. Can we say that? Okay, let me build a graph out of it and then see how do we solve the problem. So graph problems are always, typically, if you have relationships given, you can think of the problem as a graph problem. Some of the relationship problem becomes tree problem also. We have done problems where parent-child relationship are there, org charts are there, but tree is also a form of graph. Make sense? This is the application where you may not see the problem as directly give me topological sort, but somewhere if you conclude that I have to build a relationship and then print in some order, that's it. One more for you to think about, not giving you the solution. Given a program, let's say given a C program, we are simplifying it, where you are given function A calls B, B calls C, like that. Some C program is given. You have to tell the C program uses recursion or not. Yeah, so when we say there is a C program given, you have a function, each function making some other call. So this is your starting function, it makes calls to B, you get a dependency relationship. When will recursion be there? If a function calls itself, that is direct recursion, or if A calls B, B calls C, C calls A again, or there is an indirect recursion. So what you have to do in a graph, you have to detect cycle is there.
Cycle.
You say, yeah, it uses recursion. So you see, these are the problem is just a modeling, knowing 2-3 algorithms in graph, and you can map the problem to graph and say this standard algorithm will solve. So in graph, 3 algorithms we talked about: BFS, topological sort. They solve most of the graph problems. Right. So all undirected, unweighted graphs, they take care of it. There are 3 more algorithms we will do for weighted graphs. For shortest path algorithms, they are separate. So this is, but key focus is on these 3, and that's why like today's day we are spending on mastering all that, so that our base on graph is set and we don't feel scared of graph problems. So yeah, we'll take a break and then we will code these all 3 algorithms: BFS, DFS, and topological.
This conference will now be recorded.
Okay, so we are starting with the day 7 class so that we spend time in coding that here and we leverage those algorithms going forward. So let's begin with in degree, out degree of vertices. It should be easy problem now to do. So go to day 7 problems, introduction to graphs. Let's try to wind up 3 problems. We will also be coding along with you so that everyone is clear about these.
Sandeep, I see 4 problems in this area.
No, so
Am
if you
I
do
not?
force refresh, Prakash, fourth will go away. That's topological sort here.
Okay.
Yeah, so we added it to be covered that day, but we did not cover. So that is what we discussed right now. We will go and do that problem also. So you will see only first 3 working. Yeah. Okay. Okay, sure. So you are saying this is, you say this A and this is B. A is dependent on C, B is dependent on C. So here the output should be, since they both are dependent on C, so here you are saying dependency is reverse. So B is dependent on C now and B is dependent on A now. So here the output order will change because you will start with C first. Yeah. In that case, what will change? Can you change the same algorithm to work for this graph also? Okay. Sure. Correct. Yes. What you are saying is correct. So when we code topological sort, we will code in both ways, DFS and BFS. So depth first that you are talking about, that also gives one possible order. But whatever we discussed, can you apply that here also? Previously we were calculating out degrees. Here you go with in degrees. Whenever you remove a vertex, you have to go and change the in degree of this vertex will change, but go ahead and change the out degree of every other vertex. But ideally you can apply that solution here also. And second thing is, if you are given graph in this format, you can convert it to your format and solve the problem. Just a notation change, right? Yeah, so once we are comfortable with these 3 algorithms and all the ways of writing them, then solving the problem will not become a problem or issue.
Sandeep, in the first question that we did today, read and print graph, if the graph was weighted, we had to go with the matrix concept, right? We couldn't have used the list.
No, so we will spend some time, Prakash, on those things. If graph was weighted, today we are not focusing on weighted graphs, but if graph is weighted, we will go with this notation.
Okay.
List will be list of integers, it will be list of edges in all 3 notations.
Okay.
So each edge will have a vertex and a weight associated with it.
Okay.
Right? So adjacency matrix notation will not hold good beyond 1000 vertices. So if bigger graphs are there, matrix notation can work up to graph with 1000 vertices because you are taking 2D matrix of 10 to the power 6 size. It's 1000 into 1000, right? But usually graphs given are big. They say there are 10 to the power 5 vertices in the graph. Then you cannot even declare a 2D matrix. So that's why we are mastering this side, that we should be able to have dynamic graphs represented in memory. Okay guys, so we are coding in degree, out degree of vertices.
This conference will now be recorded.
In this problem, we have to create full graph. Now, 2 choices are available to you. Can we represent this graph as a adjacency matrix also? And then calculating in degree and out degree, what it will become. If something is there, this says that from A, how many edges are going?
Out degree would be the row sum and in degree would be the column sum for that particular vertex.
So if the constraint is smaller, it's easier to code in matrix way, right? But we are not going and coding because we need to practice list thing. But keep this in mind: if 100 vertices are there, why to even go and create a list and map? Simply store them in a 2D matrix. Easier calculation. Agree?
This conference will now be recorded.
Then it brings the third notation for the graph. It is called edge list. If you just remember U to V, U to V, that is also remembering full graph, right? The way we provided the input. If I give you these edges, will you be able to reproduce the graph again? Yes. So that is third notation, right? In some problem, we will see like in degree and out degree. As you said, just having edges, we can go and calculate the things. There is.
And we can put that in note also. That's
Yeah.
So
That was it.
yeah, here we can say it's list of edge we are talking about, right?
Yeah. So now we can say third is edge list representation, right? That is just list of edges. And this becomes our graph, where edges are now having either UV or in weighted graph it will have UV and W, three things.
Yeah, this time here when we go to we will go in C++ so that C++ guys can also take.
C++ though I forgot. Yeah, Amit, you will help. Input format is we read number of vertices, number of edges.
And this is having one graph or multiple graphs?
Multiple graphs.
So this is same as the print graph problem that we did just now.
Okay.
Input format is same as what we did earlier, read and print graph.
This is an undirected graph.
This is an undirected graph given, yes.
So we have to calculate degree of both the vertices. If there is an edge between 1 and 2.
So if there is an edge between 1 and 2, it will contribute in degree in both, right? But think about it. While we actually added two edges, right?
Yes.
In adjacency of U, we added V, and in V, we added U. So no extra effort we will do. It will automatically calculate 2 into X. Yeah.
Yeah.
Samit, how do we declare a graph? Vector? Okay. Something like this? Okay. But one vector is just neighbors of one vertex, right? We require list of list or array of list or map of list. Two vectors, list of list type of thing, right? Isn't it? Why? Is this a weighted graph? No. Ints are like, in this graph it is given that it is numbered from 1 to NV, right? So many ways are there, right? Or we can do, if we are going like this, then it is an int and this, right? This is your U and this is all the neighbors of U or all the vertices, right? So this is another approach. Now we have to go and read all the edges one by one, isn't it? So from U to V there is an edge. How do we represent this? G of U. G of U is a vector. Dot pushback value. And if a given graph is undirected, we have to repeat it. Question is using given a directed unweighted graph. What I'll change here? If U to V there is an edge, we just need to add that thing, right? From V to U, it is not required, right? This was just for undirected. So after this, write a function, pass this graph, and that may return you, or you can do it here itself, right? So spend 2-3 minutes of time and then this one.
Yeah. What is your doubt?
Yeah.
Yes, sir. Sir, explain how to calculate in degree.
Uh-huh.
So then explain it again.
In degree. Okay. Give me 1 second.
So in degree of any vertex is when it is coming in the adjacency list, right side. Out degree is easy to calculate. For every element, its size of graph notation is given to you.
Yes. So let's say this is the graph A to B and B to C, right? Map wise, A vertex, how many neighbors it has? 1. B, directed graph wise. B doesn't have anything. C, D. So this is ultimately what C doesn't have A, right? C has a neighbor just B, right? Let's say extended this D, then C will have B and D as the neighbor, and D nothing. So this is what this map is representing, right? There are 4 entries in the map, A, B, C, D, number of vertices, and the values are all the neighbors of A, all the neighbors of B, all the neighbors of C, right? Out degree of A is can we say directly size of this list? Think about for C. Out degree is 2, right? 2 entries are there in this list. So out degree is simply you go to G of C and dot size will give you. In degree of, let us say we are calculating B. Ultimately, you have to see how many times B appeared in this right set. Isn't it? We have to count it. Now there is no direct way of going and checking how many B's are there. So you will iterate over this list and check if B is there or not. You will iterate over this list, you will iterate over this list, right? So just iterate one time and keep adding them in an array, right? Whenever B comes, B plus plus you will do. Now this is ABCD, ultimately we'll code with 0, 1, 2, 3 or 1, 2, 3, 4, right? Is it clear?
This conference will now be recorded.
So graph construction is clear, right? Now how do we take in degree, out degree? Can I take in degree array int in degree of size what? Huh? V plus 1, NV plus 1, yeah. This is in degree array, and then we take out degree array as NV plus 1. Initially, we should have their in degree and out degree initialized to what value? In degree 0, size of in degree. Initially, we are making all zeros. Right? In Java, we don't need this because by default, arrays are initialized with 0. So now, if you want to calculate, we can say for every vertex I less than equal to NV, I plus plus, what will be out degree of any vertex? Out degree of I is equal to size of the adjacency list. How do I get that size? G of I dot, right? For int degree, what we do? For int j is equal to 0, here we have to start from 0 because it's a list. J less than gi dot size j plus plus, and we say in degree of j plus plus. Yes? No. There is a mistake in this code. This will g of, this code will not calculate in degree correctly. This should be, see, j is just the index in that list, index 0, 1, 2. But we don't want the index, we want the value at that index. How do we get that value? G of I will give the list and j will give the value. And if this causes confusion, that's the reason we prefer going with, we can write separately. Vector of int adjacency list is g of I, we know that. Since g of I is already taken, so it helps us. Little extra code is fine as long as it is readable and we are able to understand what we are doing. So this way we will calculate in degree. Because in degree is number of time it appears in somebody's adjacency list. That is what we are calculating. So now out degree is calculated, in degree is calculated. Only thing remaining is print in degree array first, print out degree array, and then give a new line post that. So this is what was expected in this problem. So it helps us clearly understand how we are calculating in degree or out degree or both for every vertex in the graph.
Sandeep, can you check my submission?
Sure.
I'm getting no error, but my output is wrong.
Sure, no worries. We'll check because small mistakes happen, which we'll discuss and it will get corrected. Yeah, so Prakash, your code is this, and we'll look at it together and see if we can help Prakash figure out the mistake. Okay. So what is this doing, Prakash?
Yeah, instead of calling the size function, what I did is I took a outer loop for moving through the graph array and inner loop to move through the linked list at GI. So
So
every
see
time
this.
in
Let's say, yeah, you are doing small mistake, which is something we have to catch. What is out degree of 2?
2,
Okay. And what will this nested loop do for 2? When I is 2,
yeah. So if we check the list for 2, it would be 3 and 4, right?
initially
So
out degree of 2 is 0, right?
yes,
Yeah. So now tell me, for, yeah, 2 has a list which has 3 and 4 in it, right?
yeah. So this inner loop will run twice because x would be 3 and then x would be 4. So therefore, I am incrementing out degree I 2 times.
Correct. Which is correct or wrong? Oh, this is
According to
correct.
me,
So
it's
you are
correct.
counting how many times it is going out. No, this should be fine then. So you are looping over the list and every time you are adding one value. So this should be okay.
And then I'm for in degree, I am just using the x. So if x is 3, I am increasing in degree of 3. If x is 4, I am increasing in degree of 4.
Yeah, fair. That looks fine. That logic. So number of edges. But this is Prakash. This is, read the problem statement. What kind of graph we have given?
Wait.
Yeah. So yeah, this logic is correct. Yeah. This is another way, guys.
Directed. Okay.
When
Okay.
when he's going over the list, he's saying from I there is one edge going to X. So I will increment out degree of I. Then I add 1 to in degree of X. So Prakash, what you could have done here is, here this could have been directly written before it, right? You could have said I out degree of I is gi dot size. Can we say that?
Yeah, but I am trying to reduce the practical complexity. See, size function will also be using some computation time,
No,
right?
size function is usually big of 1, because in classes they remember the size and they return you. Whenever you add, they increment the size. So,
Okay, yeah, then it's fine. Yes.
but it's okay. I mean, be aware of both the ways.
Yeah, if,
Yeah.
after removing also, I am getting a wrong output.
Sure. Now we will see. But you have validated what answer you are getting and what is the mistake.
I am getting in degree correct, out degree wrong.
Out degree wrong. Okay. So let's see. Out degree of I plus plus. In degree of this plus plus. When you are printing in degree. Prakash.
Sorry.
Yeah. So this is something we should start seeing now ourselves. Copy paste.
Yes.
Yeah. So yeah, be aware when we are doing copy paste, we copy paste same code. So okay.
Yeah, now it's fine. Thanks.
Yeah. Sure. Okay. Sure. Without using, you're using directly. Okay. What is this output? Okay. So you read V and E. You created vector of vector. Why two vectors of vectors? One was good enough, right? For every vertex, one in degree, every vertex, one out degree. Why vector of vector? If you have 10 vertices, it's one vector which can hold their in degree or out degree. Okay. 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 First mistake you are doing is this is not a undirected graph. Okay, then you created two graphs. Okay, in two graphs. But I mean, I'm not understanding, why do you need two graphs? Ideally, you have declared two graphs here. Why two graphs? Hmm? Okay. Uh-huh. Okay. Okay. Yeah, but ideally this assumption is ideally this thing that you are doing is reverse is wrong, right? It will not happen. If U to V there is an edge, there is no edge from V to U. This is directed graph. Okay. Oh, okay, okay. So got it. Okay. Okay. Sure. Then when you are printing, why are you sorting? Is it required? Okay. Huh? Sorting is not required. So once you have built this in degree out degree graph, then it is just the size of every list, right? Okay. Now, ideally, if I see your approach, yeah, you should just be printing size of every vertex out degree and every vertex in degree. So size of the list you need to print. That's it. And after sorting also, you don't have to print those. These values are the values of the vertices. We are not expecting vertices to be printed. We are expecting count to be printed. See what you did, Amit, when 1 was connected to 2 and 3, so you are making a list of 1's list has 2 and 3. Now eventually if you go and print 2 and 3, doesn't matter. We say 1 has 2 out degree, print the size of that list, not their vertices. So it is like the second for loop that you are doing, it's just the list size in the first, list size in the second. Size of the list, yeah. Wherever you are maintaining in degree and out degree. Yes. Okay, anybody else who needs help with in degree, out degree? You're done, Mustafa? No, stuck. Yeah, Samir, you are done? Gram, almost. Okay. Done. So you move to the next one? Yeah, great. So people who are done, just move ahead.
This conference will now be recorded.
First of all, this should be out degree. This is clear, right?
Yes, clear.
And when you are calculating in degree of any vertex, you have to update in degree of that vertex, atj.get of, because that's the vertex number.
Okay.
Plus. Here the index should not be j. J is just the index in that list. J is not the vertex.
Okay. We are counting the frequency in our degree array, right?
You're counting the frequency of that vertex in this list.
Yes. Now I got it. Thank you.
Submit and validate. Yeah, now it is giving even wrong answer. So in degree is not calculated, okay, because I did not change your in degree.
Yes.
And also make sure that after every test case you are giving additional print length. That is what was expected in the problem.
Okay.
So after printing this, there should be, because when one test case is over, print additional new line.
Hmm.
Even now this is not correct. So let's see what other mistakes are there. Creating array lists, every edge U is adding V, in degree out degree.
Sandeep, here the printing loop should be starting from j equal to 1 and in degree loop should be yeah, it should be 1, right?
Yeah, that's right. So it should be starting with 1. Yeah. Good catch, Prakash. Line 28. This one. Since he list, that should be fine for j in degree length, j in degree of I. Now what mistake is there? What error are we getting? 2 in degree of first graph is
The output is reversed. I'm not sure why. In degree is out degree and
higher.
out degree is in degree.
That's right. So first we should have printed.
Okay, so
Okay.
we are putting out degree in degree. So in degree and out degree order should be reversed. 26th and 29th.
That was the original mistake, but I fixed it in a wrong way. Yeah. So now it should be fine. And I saw one additional space also. So this is, you got it? Oh.
Yes, Sandeep, I got it. Thank you.
So guys, we are good to start with depth first search. Right. So let's talk about the concept once again. Depth first search of a graph is, if you are going from 1 to 2 to 3 to 4, if this is the kind of graph you have, first we will talk about writing a function for doing depth first search from a given vertex. Because if you are able to do depth first search for a given vertex, let's say 1, then we will call that function for every graph, for every disconnected component of the graph. Because why we are doing it this way is, we are saying a graph can have structure like this, where 1, 2, 3 are connected to each other, 4, 5 is connected to each other. So this complete thing, can I say this is a graph? Right. Now when I say do DFS with 1, we will be printing all the vertices which are reachable from 1. And when I say do DFS from 4, we will print all the vertices which are reachable from 4. So we want to think of a function, at least come up with the steps so that we all are clear what we are doing. So we say void DFS, we take graph. So which notation we feel comfortable with, that we go ahead with?
List integer.
Sorry, can you repeat, Prakash?
List of integer.
Okay, list of integer, and our graph is an array. Right, let's say we are starting with this and we say go ahead and print the DFS starting with the vertex S. So how do we go about doing DFS traversal starting from a vertex S? In graph, we also have to account for that same vertex can be seen again, because there can be cycle also. So when you are starting with vertex 1, DFS means you will go and print, it's like pre-order traversal. 1 will be printed directly. So we say first print S. Once we have printed, we should say this should not be printed again. Yeah. Mark visited. Somehow it can be an array of booleans or it can be a set. Then what should we do? Yeah, we will do that. So we come to one vertex, you print the vertex, you mark it done. Then what do you do? For every reachable vertex V from S, what should we do? Call DFS once again with same graph and V. Right? But since this is recursive, we should account for one base or corner case also. If S is not present, ideally we will call it with the present vertex. If S is visited already, compare it with pre-order traversal of a tree. What we used to do there, we used to get a root. We said if root is null, return, because we know we cannot go beyond it. Then we used to say print that. After that, we used to make two calls. Here we are writing a loop for making calls because here more choices are there. But how do you account for this visited? This array somehow we have to fit. Right? So what we can do, we can write this all thing in a helper function, and that helper function can be given an array, boolean, visited array, or you can take a set, write a helper, and that helper takes care of doing all this. So void DFS helper. This helper will take graph, this will take start vertex, this will also take a visited array. So that you modify that visited array and call DFS of H. Approach wise, let me know if anything is not clear. Yeah, Prakash, is it clear to you what is DFS and why, how we are going about it?
Yeah, so can you take an example of a tree
Sure.
and explain, because I'm still not clear about how will it go.
No problem.
Just a sort
Yeah,
of
we will.
tracking.
Yeah, sure. So we will take an example so that we are able to clearly visualize DFS and then we go and code it. Yeah, so let's pick some graph. Let's take this graph itself. So for this graph, if you see that we are visualizing, what will be the adjacency list of this graph? Let's draw some adjacency list so that we can visualize. 0 is connected to
2,
2. 1 is connected to
2,
2. 2 is connected to 0, 1, 3, 4. 3 is connected to 2. 4 is connected to.
2.
So let's consider only half component of this graph. This is what the list will look like to us. So let's say we are starting DFS from 2 here. Correct? So DFS is happening with 2. We take a visited array so that we do not print the same vertex again. So this visited array will have 0, 1, 2, 3, 4. All will be false initially. Right? Now when you started with 2, the first thing we said, we will check, is 2 already visited?
No.
Here is it visited? No. So we go ahead, we say for 2 we should do DFS. We mark it visited now and we print it. So output may 2 will be printed and this will be marked done. Correct? Then we go ahead and we say from 2 what are the next choices, we have to go ahead with that. So from 2 you will start looking at the adjacency list of 2 because that is what gives you an idea what options are there. 2 sees first option is 0. So 2 says to 0, you go and do your DFS. You are the first guy, I'm giving you the chance. 0, if he has more vertices, it will go and give them chance. So this will be going depth wise. Right. So
Okay.
2's DFS is waiting here now for one of first child to complete. So clear so far? Now when we are doing this with 0, what will happen? 0 is visited? No, it's false. So we mark it visited, we print 0, and then what does 0 do? 0 looks for its children and next options. So 0 will see that next vertex of 0 in the adjacency list is 2. 0 will make a recursive call to 2 to go and do DFS. But this time what will happen? Because 2 is visited, that boundary case is protecting us. So the guideline we are still keeping the same. When we are making recursive call, we are not making them conditionally. We blindly make a recursive call and boundary case handles returning. So 0 made a call to 2. 2 said I'm done. So we return back. So DFS of 0 made another call to DFS of 2. that call returned back immediately. Now 0 will look at what is the next adjacent vertex of 0. No other vertex. So 0 will say, hey, I'm done because I had only one child, that is done. It goes back to 2. 2 had a for loop. For every vertex it was going and calling recursively. So what next vertex will 2 pick? 1. It will go ahead with 1. 1 is not visited. So we are doing DFS of 1 now. So 1 will print himself. 1 will call all its children. 1 has only one child or one adjacent vertex which is already visited. That recursive call will come back. So 1 will say I'm done. So 2 went to 0, it backtracked. 2 went to 1, 1 backtracked. Now 2 has more choices left. 2 goes to 3. 3's DFS will print 3 and come back. 2 will go to 4, 4 will come back. Prakash, does it make sense?
Yes, but if we consider this given graph, now we have exhausted the adjacent vertices list of 2. So how do
Correct.
we reach 5 here?
Okay. So how do we reach 5 is, this is DFS for one vertex, right?
Yes.
This function will change for us. This is DFS for one vertex. When we do DFS for graph, what we do, we change this function. We will never get this input, right? We will not get S. DFS for graph will be giving us just the graph. So what we will do is, for every vertex I, we will call DFS of that vertex G and I. Does this make sense, Prakash?
Yes. So in that question, the one just that we saw on mentor pick, if the starting vertex is given 0, then 5, 6, and 7 won't be included in the DFS of that, right?
Yeah, that's why we are writing this loop, right?
No. I'm asking in the DFS of 0, only 2 will only 1, 2, 3, 4 will be there, right? 5, 6, and
That's
7
right.
since they are not reachable.
Correct.
Okay.
So when you do DFS of 0, it will go and print all the vertices of this. Then 0's DFS has completed. Ideally, it should be 0. 0's DFS has completed, right?
Yeah.
This will go and call DFS of 1 because 1 is already visited. It will return back. Hey, I'm done. It goes to 2, return back. 3 returns back. 4 returns back. For 5, it will again go and make a call. It will print everything and come back.
Got it.
Right? So this is the difference. They should be clear, like DFS from one vertex and DFS of entire graph. What is the difference in that? So here, this is how we understand.
Okay.
Urdu came online. Yeah, so with this understanding, just code it. If you need help, let me know.
Uh, for the DFS for graph, we need
Mhm.
to reset the Boolean array as well, right? Visited array.
Yes, Boolean array resetting at graph level, not at a vertex level.
Yeah.
Will it help if we take this boolean listed array as global?
You can do that. Yeah, you can do global because every time you are passing, whatever you are passing, it's same. Yes. Here I believe every language has the code given here.
This conference will now be recorded.
So let's revert it back to the visited thing and start from there. Yeah, so this is the DFS code. The component wise, what we were saying, we said we can take int C0. One more time. If visited of I is 0, I removed visited array also, it seems. Visited array of size, G dot size. By default, this will have all the values as false. If visited is false, then we go and do BFS, DFS, and then we say C++. And this is the connected components count, right? And since I made it a Boolean array, I can go and change it to Boolean and here I'll say if visited of key is true, so this is the small change which gives us even connected components in a graph. How many components graph has? That problem is not added on Mentorpick, so we'll see if we can add that as a practice exercise if people want to do. Okay, anybody, any questions in DFS, depth first search?
Yes, Sandeep. If we want to do it using iteration, is it possible instead of recursion?
Yeah, if you want to do it using iteration, you will have to use stack there. Because you need, when you are going somewhere, you need a way to come back.
Yes.
Your question is yes, Prakash. If you want to do DFS without using recursion, then you will have to use stack, and in that way you can achieve DFS.
Okay.
Yeah, Arun, you are done with the first one also? Okay, sure. So shall we move ahead to BFS now? Yeah. So what is if that changes in BFS? So again, we will go with a similar way. We can do BFS of a graph with one vertex. And then same way like we will call. So this we will make as BFS helper. We will give it a visited array also, so that we can call BFS multiple times also. We can do BFS of graph using this helper function. So what does BFS suggest us? Right. So approach of BFS is, first of all, can I say if visited of S is true, return, because we want to call this function for every vertex which is unvisited. Then print S. But usually when we do BFS, we take a queue, put S in queue, and then we say while queue not empty, printing actually we do inside the loop. That was our level order traversal. This is level order only, right? But when we have put it in the queue, question is, where should we mark S as visited? When we are putting in the queue or when we are printing?
When we are taking it out of the queue, I mean printing.
So when we are printing, if we do that, what will happen? 1, 2, 3, 4, 5. Now you see, if you are putting 1 into the queue, let's take 1 out of the queue and print it. And then you mark it visited. Now you put 1 will put 2 and 3 also, right? Now you take 2 out of the queue and print it. So 1 is visited, 2 is visited, correct? 3 is not yet visited even though it is there in the queue. Now what will happen? Ideally 1 had put 2, 1 will put 3 also, isn't it? Wait, let me correct it. So when we are having this as a graph, let's take a visited array and let's take a queue. First we put 1 into the queue. We are not marking it visited. Right now everything is unvisited. This is 1, this is 2, this is 3, this is 4. Now when 1 is taken out, 1 will be printed as well as marked visited. What will 1 put in the queue? 2, 3, 6. Don't assume this edge. 2, 3 and 6, 1 has already put. Now what do we take out of the queue? 1 is printed. We take 2 out of the queue, print it, and now we mark 2 visited. What will 2 put in the queue?
3, 4, 5.
So 3 is coming once again in the queue. That means we will take it out and we will print it once again. So what if we can put some check in place so that queue never gets an entry again? If something goes into the queue, we can take blindly out and print it. So when we have put S in the queue, mark S visited. Now we take front out of the queue, front element. Here we can print because we are anyways guaranteeing that any element put in the queue is one time only, so we can print that element. Now, for all reachable vertices of print element V, for all reachable vertices of V, what do we do? Put in queue, mark V, mark visited, but you put in the queue only if for all reachable vertices U of V, U is the reachable vertex, V is the actual vertex. If U is not visited, only then put in the queue and only then mark it visited. So this is making sure we don't put any vertex, even if it is visited, we never put it back in the queue. Yeah, level order is not recursion, it's just taking the queue and working with it. Oh yeah, ideally reason I put it helper is because we will be calling it from BFS of graph. So that will be BFS. Yeah, we can call it BFS for a vertex. So approach wise, this is level order, but in graph, one additional thing that comes into picture is the visited array. That is something we have to manage.
Declare it outside and just use it.
That's right. The visited array we can either have global, and it will be same thing. Yes, it's just avoiding one more parameter from the function. Yes. Ideally, graph also we can declare globally. Yeah. So let's code BFS.
This conference will now be recorded.
Yeah. What is your question,
Yeah.
Prakash?
Can you go to the Visual Studio Code that you written?
Yeah.
Yeah, in this line number 165, in every recursion, won't this queue will be overridden? Shouldn't be it a global queue?
Good point. This queue will not be overridden ideally if you see. By the time this while loop gets over, will the queue become empty or not? When we are running this code, at the end of it, queue will anyways become empty. So anytime when you are coming, this queue you have to take again, which is perfectly okay.
Okay, yes.
Sorry? Yeah, you can also declare it globally. Because every time you are filling the queue, in one test case, you are filling the queue and emptying also. So same queue can be reused, yes.
Sandeep, that visited array is already defined?
Yeah, visited array will be passed by the main function of BFS, where we should define it and pass it, like we were doing for our DFS.
Yeah,
Here,
but here the C# code is hidden, na? So that's the reason I was asking.
no, visited array, then it is not defined for you. You have to write
Okay.
that.
Okay.
Yeah, you are given a graph, that's it, right? So you are given a graph, Rahul, you have to start from there. There is nothing visited array that we are giving, so you have to declare use it. The way you did in DFS, did you do DFS?
Yeah, it failed. I'll check. Like I'm trying it in local actually.
Okay, sure. Anybody needs help in BFS breadth first search? You're getting partial output? Sure, we'll take a look at your submission. So the all test did not run. It's running.
It's running, but actually I just submitted.
You submitted and went back?
Some error.
Oh, okay. Then it might be some issue at our back end. Yeah, today there is some issue going on in so let's see. Okay, so you are starting with BFS of entire graph. You took a visited array, initialize the visited array with all false, and then you are doing BFS helper for all visited. Okay. But when you are doing it for graph, won't you call BFS for all the vertices? It may be a disconnected graph also. Right. So we'll have for int I0, I less than g dot size I plus plus, and then you will make this call for. Oh no, this is
Actually, S is like given.
oh, S is given. Okay, this is given a B. So you you are just writing the function. Sure. Then we don't need that. Okay, so this is fair. So you are sending it. If it is visited, you are returning true. Otherwise, you are taking a queue, push S in the queue, but where are you marking S visited? We discussed that when we are putting in the queue, we mark it visited. Visited of S is true. Then you take it out, print it, remove it from the queue. Yeah, here you are anyways putting it. Fine. So this was missing for S. S was not marked visited earlier. So if you anytime come back to S from any other vertex, you will end up getting one more extra value in the queue.
But not actually getting all the values. I'm getting part of it.
Okay, so let's see, there may be other issue. So now you are getting all the vertices adjacent to S. But why S?
Because we have put S.
No, but every time in this loop, you will not get S out, right? Either you make S dot is equal to Q dot front, whatever vertex you have taken out, you have to take adjacent vertices of that. So this S should be overridden again and again. So that was the issue, because you were taking out and printing directly, but you were leveraging same S from the beginning. So now it should be fine. Oh yeah. So we can just make it S. Yeah. We throw an error. Yeah. So yeah. So that's the issue. Okay. Anyone else needs help with BFS? Arun, you are done with topological sort? No. Okay. Okay. Om, you're done. Okay. Love, you're facing issues in compilation. Semicolon expected. Return type required. Line number 16 does not have a semicolon. Yeah. Prakash,
This
you're not.
conference will now be recorded.
Sorry.
Yeah, Prakash, can you speak now?
Yes. Hello.
Yeah, now you're audible.
Okay. Yeah. Did you ask a question?
No,
Because
I
was.
just saw your message here. That am I audible?
Oh, okay, that was earlier when I had it out.
Okay, Pranav, no issues. If you are done, yes, then fine. You're done? Figuring out. Need help? Huh? You did not submit. Okay, so you're thinking about your logic. Yeah, feel free to do that.
This conference will now be recorded.
Okay, guys, do you see any bug in this code? If a vertex V is visited, return from here, otherwise add to the queue and mark it visited. While queue is not empty, this is the same mistake as we fixed just now for someone. Prakash, here, what will be the value of vertex in this while loop?
Okay, it would be the one I sent earlier only.
So what you should do when we are taking this out, you should update it so that we are using that for its next neighbors. Otherwise, you are only going with the neighbors of the first vertex, and that is what you are seeing in the output.
Yes.
Right? Yeah. Now it should be okay. Yeah.
Yes. Okay, so one question here, since DFS
Yeah,
and
Prakash.
DFS both have been covered. So I shared one question with you, that step
Mhm.
problem that every day's number can be either added, we can add 1 to it or we can multiply it
Mhm.
by 2. So
Correct.
how did you suggest that it can be solved using BFS? I mean, in what cases shall we use BFS? In what cases shall we use DFS? Can
Okay,
you?
because that was you wanted to find minimum number of steps, right?
Yes.
So it's the shortest distance, minimum number of levels that you have to cross to reach there. Yeah, we will talk about some problems on that now.
Okay.
Yeah. So I have one such problem added here for people to try and do. And initially, if you remember, when we introduced queue, we talked about that queues are applicable or useful in scenarios like level order traversal as well as shortest paths, where you want to find minimum number of steps to reach somewhere. Right? Okay. In this, if you are printing the paths, yeah, because when you go back, all the paths starting from one vertex to others. Yeah. Now let's take a look at one more thing. We talked about depth first search, right? Now a question for you is on depth first search. If you have this as 1, you have 2, let's say 3, 1, 2, 3, then here to 4, 4 to 5, and you can reach 2 to 5. Depth first code we are all clear about, right? If I do a depth first from 1 and imagine the adjacency list is like 1 has 2, 3, because order matters, 2 has 4 and 5 as adjacent vertices, 3 has 2, 4 has 5, and 5 doesn't have any next vertex. Correct? Now think about it, the DFS code that we have seen just now, the previous problem, in this case, where were we printing the value? Before visiting the children, right? Let's say if we are printing the value afterwards, then what will happen? It's sort of reverse DFS if we try to do, what will happen? You can start from a vertex, let's say we are starting from 1. So when we start with 1, what do? This time we are not printing, but we are marking 1 as visited. Okay, so 1 is visited. We will print it later. This is like post order traversal. We say don't print right now, print it after its children are done. Okay, then what will 1 call for DFS? 1 will make a call to 2 now. What will 2 do? 2 will mark visited and say let me call my children. So from 2 the children are 4. The order is, it is first going to 4. That's where we got in depth. 2 makes a call to 4. What will 4 do?
Call
Mark
5.
itself
Then
visited. Make a call to 5. What will 5 do? 5 doesn't have any children. So 5 will first mark it visited. 5 will have a for loop to call DFS for its children, but all the children, none of the children are there. So kind of we can say DFS for all its children is done. So what will 5 do now? 5 will print himself. After printing 5, because that was the last thing after for loop, now 5's function call is returning. We are backtracking to 4. What is the next choice that 4 has? Nothing.
Printing itself.
For loop is getting over. What will 4 do now? 4 will print himself. Done. 4 goes back to 2 because 2 is one who invoked 4. What will 2 do? What is the next choice 2 has? 2 has 5. 2 goes to 5. 5 is already visited. The base case that we had written, it will come back. It will say, hey, I'm already done, so I don't want to do anything. Now 2, all the children of 2 are covered. 2 will print himself. 2 will go back to 1 and say, I'm done. What will 1 do? It will call 3 now because 1 had another choice as 3. It goes to 3 and says, you do DFS. What will 3 do? 3 doesn't have any unvisited children. It goes here, comes back. 3 will print himself and then return back to 1. And we print 1 here. This traversal that we got back, this is reverse topological. Everyone agrees? Because what we did, we were printing something in the end. We were saying first we are giving chance to all the children, because through children it will keep going. So ideally, if you see it keeps going there, all the dependencies, if there is anyone who is pointing to 1, we are giving it a chance first to print itself. So ideally, slight modification in DFS gives you reverse topological sort. In the end, just reverse it and print it. So what we can do is, if you want to get topological sort, rather than print, what should I write here so that I get reverse topological sort? If I keep printing, I'll get it reverse, but I don't want reverse. Add it to either stack or any list so that we can print that in the end. So here we can also pass a list to it, or we can declare a global list. But DFS with a slight modification gives us topological sort. That is a DFS way of getting to topological sort. But the question is, if you want to do topological sort of a graph, how do you identify which vertex shall I start from?
Which has n degree equal to 0.
One option is which has n degree 0. Let's begin with that. We get the answer. Correct? Or second is, this algorithm of DFS says you start with any vertex, doesn't matter. The answer that you will get will be reverse topological sort. Even if you start with 2, you will get reverse topological sort because 2 is printing itself in the end. 2 is giving chance to others, so most likely all the dependencies of 2 will be done and then we will revert back to 2. But when you start with 2, there may be some graph, like when you are starting with 2, will you ever print 1? No. In that case, we have to do DFS of entire graph. Start with every vertex. Order doesn't matter. Topological sort will absolutely come correct order. Doesn't matter which vertex you are starting from. But you follow that trend of you are calling DFS for every vertex. So this is like DFS way of doing topological sort. You can start with any vertex if you start with 2. But when you are done with DFS of 2, you have to make sure you are starting with next vertex also. Order doesn't matter. After 2, you can go with 1 also, you can go with 5 also. I'm saying the order of vertices that you are giving to this algorithm doesn't matter. But you have to do DFS with every vertex because sometimes if you are not choosing the right vertex, some vertices may not be covered. Now, every output will be correct output. Let's see. So let's say we will first start with 2, then we will go with 3, then 1, then 5, then 4. This is clear that we have to start topological sort with every vertex, like we did DFS for the graph. So let's start with 2. What will happen? We go to 2. 2 says I will not print myself, but I am visited. Let me give a chance to people who are reachable from me. 2 goes to 4 first. We go to 4. 4 also marks it visited, but does not print. 4 goes to 5 now. What will 5 do? Market visited, print himself. Now 5 doesn't have any children. 5 goes back to 4 and say I'm done. What will 4 do now? 4 will print itself. Printing is, here we are saying it will add himself to the list or stack. Now 4 says I'm done. 4 goes back to 2. What will 2 do? 2 had one option, this. 2 will go and explore second option, but that will immediately come back. Now 2 will also print. So topological sort from 2 has given you 2, 5, 4. But you are saying I still missed something. So let's continue topological sort with 3 now. What will happen? 3 will make a call to 2. 2 is already done. So 3 says I will also print myself. Now 3's topological sort is done. Go to 1. 1 says okay, I am starting, but both my children are already done. So let me print myself. You start with 5. 5 says I'm already done, not required. 4 says I'm already done. You see the output that you got even now. It's the same topological sort. So we are not focusing on those graphs where multiple topological sorts are possible. It's possible that one graph has two topological sort. Or think about if there is a totally disconnected graph, no edges in the graph, how many topological sorts are possible? No one is dependent on each other. Number of vertices? No. How many topological sorts are there? All
Sigma n maybe?
No. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1. You do it in any order, doesn't matter. Right? So topological sort, it's not like there is only one topological sort possible. But whatever problems we have put, we have made sure the test cases are written in such a way that you get only one topological sort for a graph. So DFS way of topological sort is clear. It's a small tweaking we can do. We can achieve this using BFS also. Whatever algorithm we discussed, let's try to fit that in BFS code and achieve the same. Previous algorithm, if you remember, we were losing time in finding that vertex, which has in degree of 0, right? Every time we were looping over that. So what changes we do? For now, we will assume the graph is connected and we try to get a topological sort using BFS. Let's say top sort. First thing that we do is, here we don't need the start vertex. First calculate out degree of all vertices. This step we are clear about, right? Now in BFS, what we used to do? In breadth first search, what we used to do, which we used to use a queue. Let's use queue. Out of all these vertices, when we are calculating out degree, can we also identify one vertex which has out degree 0? Or one loop over that can give us that vertex. So let's treat that as a start vertex. Oh, sorry, in degree. Yeah, thanks for correcting. So we are finding a vertex. Find vertex with in degree 0. And let's call that vertex S. So let's start the breadth first search with vertex S. Because once S is out, we do not care about S anymore. Correct? Can you go ahead with the DFS and suggest what changes will make it topological sort? Search we want to avoid. So what we will do? What was our strategy? Get the in degree. You got the first vertex. Push S in queue. Mark S visited. So far, we just identified the start vertex and we are assuming there is one start vertex. Now what do we do in normal BFS? Take S, take V out of Q, print V, pull children of V, unvisited children in in Q. We have to do some additional steps also for our topological sort. In topological sort, we talked about when we start with one vertex, if we have printed the vertex, that means one dependency is over of all other vertices which were reachable from here. So what is that step? Decrement the degree of every child, right? For every child C of V, can we say in degree of C, or we do minus minus? Either way is fine. Oh, its terminology is becoming confusing. Okay. Okay. Okay, sure. We will talk about that also. Right now, we are going with the flow that we discussed earlier, so that algorithm once we see clearly. Now, when you said in degree of C is minus minus, only then we put, okay, children C of V. We put a child in the queue only if its in degree becomes 0. How about doing that? You took one vertex, printed it. That vertex is decreasing the in degree of every vertex. You do that over here. If any vertex is becoming in degree is becoming 0, only then we bring it in the queue. Ideally, we will not even need visited array. Think about this. If in degree of C is 0, nothing can evaluate it. Will this be helpful? Yes. We will see. We will see with an example also. So let's see what we are saying and let's validate also. So this graph that we were looking at, we can start with this graph and evaluate whether BFS can give us this order or not. Here, let's do in degree array calculation for all of these. No, this is a bad example. We need directed acyclic graph. We need little bigger one. You find online. Let's take geeks for geeks graph. Yeah, let's pick this. And what is the in degree of every vertex? 0 has in degree of 2. 1 has in degree of 1. 0, 1. 2 has in degree of?
1 has in degree of 2.
1 has in degree of 2. Sorry, yeah. Yeah, 2 has?
1, 3 has 1. 4, 0, 5, 0.
5 has 0. Now here if you see there are two topological sorts possible. But we are going ahead and saying we will print any one of them. That should be fine. So what was our first step? Calculating this. Every one of us is clear. After we have done this, we also identify any vertex. Let's say we identified 5 is the first vertex whose in degree is 0. We put 5 in the queue. So this is our queue and we have put 5 in the queue. And we are not even taking a visited array. We start from there. Now what do we do with 5? Take it out, print it, and now go to its children and update their in degree. So if you go to the children of 5, who are the children of 5? 2 and 0. 5, 2, its in degree becomes 0. The moment its in degree becomes 0, put it in the queue. Ideally, we could have done one more thing, small thing. Initially, we identified only 5 as the start vertex, right? Initially, whichever vertex at the time of calculating the in degree, whichever vertex have in degree 0, let's put all of them into the queue. so that from there, if more dependencies are getting reduced, then we will start getting those, right? So initially assume 5 and 4 were put in the queue. Now 5 has put 2 in the queue because 2's in degree has become 0. From 5 we go to 0, 0's in degree will reduce to 1. This is the effect that 5 has done. 5 has printed himself, updated the in degree, whichever vertex got in degree as 0, put that into the queue. Now what will 4 do? Print itself, whose in degrees 4 will decrement? For 0 and 1. So 0's in degree becomes 0 and 0 comes into the queue. For 1 in degree is becoming 1, 1 doesn't come into the queue. Now what is the next vertex we are getting with in degree 0? 2. We print 2, whose in degrees we reduce? 3's in degree becomes 0, 3 also becomes a candidate to come into the queue. Right? Now 0 we take out, print 0, whose in degree 0 will reduce? No other vertex 0 has edge 2. So 0 is gone. Now 3, print 3, whose in degree will 3 reduce? 1. So make it 0, 1 also comes into the queue. In the end print 1, and 1 doesn't have to reduce anybody's in degree. This sorting, this order that we got, is this topological sort? Now the question comes, earlier we were talking about V square plus V plus E was our time complexity. Ideally we can get rid of V because V square is better. V square plus E was earlier time complexity. Now the question is, what is the time complexity of breadth first search? Because ideally we are doing breadth first search and we are doing calculation of in degree array. So what do you think is breadth first search time complexity? Only V plus E. Okay, that is what Satyam is saying. V plus E is the time complexity of breadth first search. Everyone agrees with that? This is our breadth first search code. And see, we are taking every vertex once goes into the queue for connected graph. If it is a disconnected graph, we anyways make sure through loop we are putting everything. So every vertex goes once inside the queue and it comes out and we print. So vertex V is certainly there. Even if there are no edges, we will call BFS for every vertex. Now what happens for a vertex? From that vertex, we go to all its adjacent vertices, we go to their adjacent vertices. So what exactly we are tracing? What this for loop is doing for one vertex? All edges of that vertex. We are running this loop for every vertex. So again, this is a question like first time it may be taking E1 edges, second time E2 edges, overall E edges. And we may call this function for every vertex. So this is V plus. Now whatever topological sorts we have come up with for BFS, it has V plus E for BFS plus another V plus E for in degree calculation. So which is big of V plus E only. Right? What is the time complexity of DFS? Okay, yeah, that is a confusion that usually arises. If this loop was E, capital E, then we agree it would have been V into E. But the challenge here is this loop is not E always. For one vertex, it's the edges of that vertex. It's a small part of the capital E. That's the reason we are not blindly saying it's V into E. And this becomes tricky to understand in graphs. Yes. Right? Makes sense? What is the time complexity of DFS? Depth first search. From every vertex, we are covering all its children. From next vertex, we are covering all its children. So there also it is V plus E is the time complexity. What is the space complexity of both? What is the space complexity of BFS, breadth first search? Every vertex we are putting into the queue, order of V. Because worst case it may happen that one vertex is connected to all other vertices. Right? And all other vertices land up in the queue. So that is the time complexity. In DFS, Not essentially. In best case, it may happen if one vertex is connected to two, one will put them in. You take one vertex out, it puts one more vertex. It may happen that sometime it's the kind of, at any level, what is the maximum number of vertices. So best case can be every vertex is putting just one more vertex. That can be the best case. DFS is also V plus E, because for every vertex we call DFS, and then space complexity will be how much?
Because we are taking
Visited array is in there in both. So visited array time space complexity gets added to both. But in DFS, extra thing that gets added is stack. So what will be the depth of the stack in worst case? All the vertices, because we keep following all the edges to one vertex to the other. So the distance between those,
is it vertices or edges?
think about it, it is vertices or edges? All the vertices. Recursive call happens because of vertex or because of edge? Think about it. Recursive call happens only if there is an edge. If there is no edge, recursive call will not happen.
Even though it's not connected.
There is a possibility there are three vertices and you do DFS of 3. Best case is this, no recursive call. You just make a loop, you call mark visited, print, come out. For this graph, for this graph, just the length of this path, right? And what is the worst case length of any path in a graph with V vertices? How deep the path can be? All
V.
it's V minus 1 ideally.
Yeah, V minus 1, yes.
Because this is 1, 2. Right? Yeah, so this was BFS, DFS, and topological sort. Now, all these things that we talked about, they have applications on various other problems. Some problems are just matrix problems, not the graph problems. There also they are applicable. Those problems we have added on mentor pick for practice. One such problem is, you are given a matrix. By default, a matrix can be treated as a tree or a graph. We know that. So in this matrix, we put ones, zeros. Let's say from any vertex, you can go in 8 directions. Any vertex will have worst case 8 neighbors, right? 3 above, 3 below, to the right. In this problem, it is told, count the islands in this matrix. 0 represents water, 1 represents land. How many islands are there in this matrix? 2 islands. First island is this, second island is, how many components are there in the graph? Right? How did we count components in the graph? We called DFS. Can we count component using BFS also? Yes, anything is fine. So here what we do, let's go to 0. It says 0, it's water, don't call DFS. 0, no. Here it is 1. Let's do DFS on this matrix starting from here. When you do DFS, this time your adjacent children in matrix are directly known. You don't have to refer to adjacency list and all. Because matrix, you know, right neighbor, down neighbor, left neighbor, you can calculate their indices. Those are your choices to proceed. Mark this vertex as visited. For visiting, for a matrix, what is a data structure we can take to mark any cell visited? Another matrix. Here the only thing is the visited matrix that we take is another matrix, right? So another matrix you take, you mark it visited. Then do DFS here. This also becomes visited. This also becomes visited. This also becomes visited. After that, there are no other elements, because if it is 0, that will be one more base case. You immediately come back. So first time when you made a call here, you marked everything visited. Then you come here, Check in the visited array, is it marked true or not? If it is not, do a DFS again. How many times you are making a DFS call, that is what you will decide. Will decide the number of connected components. It's just that that problem we did in graphs. Here we are dealing with the matrix. But algorithm and steps remain the same. Second problem is you start from this place. 1 is representing there is a path, 0 is representing there is no path. Starting from a cell ij, reaching a cell xy. Yeah, there are two varieties. One we say, first question is there a path? You start from this place, go in all the directions. If you do DFS, that first you keep going. If you hit that vertex, then you say there is a path. Shortest path, how do you find? Level order. So when you are here, shortest path length is 0 because here to here it is 0. All the nearest vertices, you will say we can reach there in one step. From there, if you start expanding 2 steps, so if you just start remembering the level also, anywhere you reach, then you will get the shortest path there. Right? So there are some problems on matrices that if you try to see matrix, you are moving in either 4 directions or 8 direction. You try to see that as a graph. People say this is implicit graph. Graph is not explicitly given, but you are kind of moving to neighbors. That's the one last thing is if graph has a cycle, let's say undirected graph has a cycle or not, you have to tell that. So if directed graph has a cycle, that is what we want to tell. Can we do it BFS way? Or sorry, DFS way, depth first way. Given graph has a cycle or not? It's a directed graph. Can you use depth first search to tell whether cycle is there or not? Okay.
When you get or hash map, when you get a collision.
Okay, so you will start from which vertex?
Vertex 1.
Let's say we start from vertex 1.
If it's listed, then go to next.
Okay.
2.
Okay.
And then 3.
Okay.
And then 4. And when you come back from 4 to the next depth, it will be 2 again. So
We have
each time you are pushing visited nodes into a hash.
Okay, let's say you go 1 to 2, 2 to 3, okay, then 2 to 4 and 4 to 1. There is a cycle now. This is a directed graph which is connected for now. Let's say there are no separate components. If separate components are there, same thing you will repeat for every component. Start point is not given. You are given a graph and asked, does that graph have cycle or not? Whenever we revisit a visited vertex, that's where we say there is a cycle. When coming back. Yes. So when you are at 1, let's do DFS with 1 and mark 1 as visited. Go to 2, mark it as visited. Anywhere if you are going down, if you encounter a visited node again, can you say there is a cycle? Right? When you come to 3, you mark it visited. But when you go back from 3, you mark it unvisited also. When you go back to 2, you mark it unvisited also. Right? But from 2, you have another option. You go here. From here, you go back. Then you say this is visited already, so there is a cycle. Right? So this is the idea. Again, this problem is added on Mentorpic, but it's an application of BFS and DFS. And
why do we mark it unvisited while moving back?
Good question. Why do we mark it unvisited? Any reason why we are marking it unvisited?
If we come back from 3 to 2,
Huh?
from 3 to 2, if we come back,
Yeah.
if it's already visited, then it won't go explore other.
Yeah. So give an example for that.
Here it comes from 2 to 4, and then after 4 is visited, then we go back to 2.
Yeah.
And if it's not marked unvisited before, then we won't go to 3.
Okay. Yeah, that is one example. Will this example serve the purpose? Cycle or not?
Is it an undirected?
No, this is directed graph.
Cycle is
No cycle is there? No cycle. So let's follow the steps. Come to one, market, visited. 1 goes to 2, market, visited. Go to 4, market, visited. 4 doesn't have any other choice. Go back. 2 goes to 3, market, visited. 3 to go 4. 4 is already visited. We say there is a cycle. Exactly. So that is the question we are answering. If you do not mark it unvisited, when you are going back, so ideally what we are saying is if you are coming down this path, from their path, if there is a back edge is in your ancestor chain, if you are going back anywhere there, that is when you say. So when you are unwinding from here, going back from here, now the chain that you have followed so far, now these are visited, not this. So this is an example where we say if you do not mark unvisited, you will see false results, wrong results. Does that help, Prakash?
Yes, Anil.
This problem will get tricky in undirected graphs. If graph was 1, 2, 4 and 3. If this edge is not there, imagine. Now there is a cycle? No, but what you will do, you will start from here, from first node. You will say visited. You come here, visited. From here there is an edge back because this edge is both sides. So we will end up saying, yeah, there is a visited vertex we are going back to, so there is a cycle. How do we avoid this situation? From 4, if there is an edge, then it's a cycle. But from 2 back edge to 1, not a cycle. Yes. So the parent, if there is an edge back to the parent, then we say there is no cycle. And we have to somehow track which vertex we are coming from. The helper that we wrote, we used to pass what is the next vertex for which we are doing. You also pass a parent vertex along with it. Now the child knows that he has to consider all the back edges, but not to the parent. So that one condition will make it work. So cycle detection in directed as well as undirected graph. Ideally, if you see, they are both BFS, DFS applications. Minimum 3 elements? Yes. With 2 also there can be a cycle. In case of undirected, yes, there should be minimum 3. But in case of directed, 2 can also have. Then we are introducing separate edges. In directed graph, we differentiate edges. In undirected, if you have 2 vertices, you can directly say no cycle. Prakash, one question is pending. He says, how do you get an idea where you are starting from a number? And this is the problem we brought yesterday, right? That if you are going from n to n plus 1 and 2 into n, these are the 2 choices you have. This question is, how do you get an idea that I should apply Q here? You want to find minimum number of steps to reach from 1 to n. An example we were taking yesterday is 8. Everyone remembers this problem? N is given, starting from 1, you can do 2 steps. Either you can add 1 to it or you can multiply 2 with it. How many steps will it take for you to reach n? And you are looking for minimum number of steps. Can we use DFS here? Depth first search, recursion, backtracking approach. You make a call to left, make a call to right. Take the mean of both. That is the answer. 1 plus mean of both. Can we use breadth first search here? Level order. Here to here, 1 step. At here itself, if you get 8, you are done, right? So here to here, 2 steps. So level we are tracking. So this is what I was saying to you, Prakash, yesterday, that when we do breadth first search, the shortest path from root to any vertex, you find it faster. Because even if it had 20 more levels below it, you are not going depth, come an unexplored path, because if it is landing at the last path, then DFS will take longer time. Breadth first will just find in number of levels that it has to traverse. Is it clear? And this problem can be there in form of a matrix. In matrix, 2 cells are there, find the minimum steps, or it can be there in the graphs, or it can be there without even graphs being there. This problem did not have any graph in picture, and no tree, no graph. Yeah, and day 10 it is, right? I have included one such problem. Just a moment. Maybe I'll have to force refresh. Similar problem that Prakash had. There is an advanced version of that I have put links for, link to. Are you able to see in today's class description any links? Yeah. Down to 0 is a problem of that category, and night moves is a problem of shortest path. Minimum night moves to reach one cell to another. This is on 2D matrix, again a BFS problem. This is if you are starting with n, there are some operations you can perform, and how many minimum steps you can reach to 0. So these two problems I have put as a reference link which you can attempt and try solving. Right. Any questions? So graph wise, can we say like we feel comfortable? Right. So these three algorithms are key. If you are able to code them with ease and code with various graph notations, stick to the simplest one where you are making less mistakes, and you can solve graph problems with ease.
Sandeep, there are some problems where backtracking is also possible, BFS is also possible, DFS is also possible.
That's right.
So how to come up with solution? I mean, which one to use and which one would be the correct one to use?
Good question. So if you have BFS and DFS way of solving a problem, which one we should prefer? Breadth first search, because it doesn't have any recursion overhead, easy to code, just use a queue. So that's a simple answer, Prakash, that breadth first search you can prefer if both of them you are convinced that go and solve a problem. Second, if you have a problem of finding minimum distance, then for sure go ahead with breadth first search. That's to you that this problem has direct application of queues. In unweighted graphs, Q or BFS is the best way to find the shortest distance.
Okay, and another question is, like today we consider topological sort, right? So first you provided a DFS way, and then we also discussed a Bradford search way. So let's say I'm given a problem and I come up with a DFS way. How to know whether a BFS solution can exist as well? Is there some
Most of the graph problems have both the solutions possible, and it will come with the practice. There is no simple thumb rule that we apply generically, like this problem is BFS problem or DFS problem. So it depends on case to case basis.
Okay.
In interview, no, people do not push you to say like give me BFS solution only. In interview, they give you a problem. Sometimes you identify the pattern, you say I will solve it using DFS. If somebody says, can you avoid the call stack that version is taking, can you optimize it further? Then you think, okay, can I go with BFS? Make sense, Prakash?
Yes. Now, in traveling salesman problem, we use backtracking, right? So how do we discard DFS and BFS there? That these two algorithms won't provide us any solution.
Okay, traveling salesman is a directed graph problem. Sorry, a weighted graph problem, right?
Yes.
Yeah, we will talk about weighted graph where we are parking for today so that it doesn't confuse people. So we will do weighted graph problems also where we find the shortest distance. There BFS doesn't help.
Okay.
Yeah. When do we know? We have to apply topological sort. Okay. If you hear some sort of dependency, some sort of ordering in the output that is required. So dependency we talked about, Maven, Makefile, we say these nodes are dependent on the other node. We cannot do these. So dependency is one such case. And second such case is the dictionary problem that you saw, alien dictionary. It says we are giving you some words, make a graph out of it. Sometimes it depends. You just generate a graph and say which order we are getting them out. Mainly it is dependency that topological sort comes into. There are a lot of online coding contest problems which say we are organizing an event, or a person is traveling to US, he has to do 10 things, and we are giving you the dependencies of that. Like he has to apply for passport, then apply for visa, and this dependency is given to you. He cannot apply for visa until unless passport is there. When we are giving you all of this, can you generate an order for that person so that he can go and apply or go to US directly? So problem statement, you are able to visualize 10 things given, order given, which one comes before first. Now you make the graph, you give the order. So dependency is again the common thing. Yeah. Any more questions? Okay. Cool guys, then we will meet on Wednesday for doubt clearing. So these graph problems that we have left on mentor pick, give it a try. You can solve more problems on interview bit also. If you feel comfortable, you can go and look at the graph section. Level order and DFS should be directly available there for you to solve. So this is like, do more practice in graph. Once you have solved 10 to 20 problems, you will feel much comfortable. Right? And if you see, most of the people, the mistakes they were doing was mainly because we are going in a map. There is a list. From list we are getting the values. That syntax is something that we need to be comfortable with. Algorithm wise, it is backtracking as well as level order. That's the only thing that we are stepping up to now. Yeah, we calculate on Saturday morning. So they will be accounted for next week. Oh, you are saying the message that I sent. Okay. Okay, no, we will include Saturday, Sunday. So now if you see, there is another sheet that has been added. In that sheet, if you see, we have captured whatever were scores for week 1, Saturday morning. So now whatever you are accumulating, it is counted for week 2. So that's the way we will track. Okay, no, we will count that. So that was a mistake from my side. Should have written like whatever score is last week. I just wrote for the algo for first week only, not for the next weeks. Okay, guys.